Imagine a universe that has just been born, only a few 100 million years old, an era when the first galaxies were forming. Thanks to the James Webb Space Telescope, we have made discoveries that transport us to an ancient era. Before you is a universe in which each small point of light is a galaxy, a vast cluster of stars, planets, and mysteries. Among these countless galaxies, some are so distant that their light has taken billions of years to reach us. Studying these distant galaxies is of great importance, as it helps us understand the early stages of cosmic evolution and the formation of structures in the universe. This spring, astronomers using the JWST were able to observe the oldest universe and discover galaxies that existed more than 13 billion years ago. One of these discoveries refers to galaxies with redshifts between 9 and 11. But what does that mean? In short, redshift measures how much the light from these galaxies has been stretched by the expansion of the universe. The greater the redshift, the further back in time we look. The light from these newly discovered galaxies began its journey when the universe was less than 1 billion years old. At that time, our Milky Way was just beginning to form, and only the first stars illuminated the cosmos. These galaxies are not only incredibly distant, but also incredibly young, allowing us to glimpse the formative stages of the universe. So, how did galaxies like ours originate and evolve over billions of years? Let's discover it. In the depths of space, hidden among countless stars, is Sears 43833. This galaxy, at redshift 876, transports us to an era when the universe was less than 600 million years old. Its light, traveling through the vastness of space, provides valuable information about the early stages of galaxy formation. Looking further, astronomers have approached Sears 16943, an even more distant galaxy, with a redshift of 11. For this galaxy is one of the oldest ever observed, emitting its light when the universe was only 400 million years old. The study of such distant galaxies helps us understand the processes that led to the formation of the first stars. Finally, MAX 0647DJD appears before us, observed with a redshift of 1017. It has taken more than 13 billion years to reach us. Its discovery has been possible thanks to the powerful capabilities of the JWST, which has revealed its complex structure and provided information about the early universe. But what is redshift and why is it so important? Let's imagine a car moving away from us. As it moves away, the taillights appear increasingly red. The light from distant galaxies stretches and shifts toward the red end of the spectrum. The greater the redshift, the more distant and ancient the galaxy is. Redshift is an essential tool for astronomers, as it allows us to measure the distance to these galaxies and their age. The light from these galaxies began its journey billions of years ago, creating a snapshot of the early universe. By studying galaxies with different redshifts, we can reconstruct the history of cosmic evolution. Distant galaxies are not just distant objects. They're time capsules that allow us to glimpse the early universe. These discoveries address fundamental questions about our existence. How did the first galaxies form? What processes drove their evolution? And what does this tell us about our home, the Milky Way? The discovery of these distant galaxies has been possible thanks to two important observation programs. These programs use the advanced capabilities of the James Webb Space Telescope to observe the universe more deeply than ever. The first program used the discretionary time of the director to focus on the observation of galaxies with high redshift, under the direction of the principal investigator Pablo Arabel. The objective of this program was to study the early universe in search of galaxies formed a few 100 million years after the Big Bang, focusing on specific regions of sky. DD 2750 successfully identified several ancient galaxies, including Sears 43833. The second program was part of a general observation program led by Principal Investigator Dan Company. This program aimed to perform detailed spectroscopic studies of known high redshift galaxy candidates. The GO 1433 program was instrumental in confirming the redshifts of these galaxies and studying their properties in detail. As part of this program, the team observed two other objects and obtained valuable data on their composition and structure. The JWST used two of its most powerful instruments, the NIR SPEC and the NIR CAM, to perform these pioneering observations. Let's take a closer look at how these instruments work. The NIR SPEC, or near-infrared spectrograph, is designed to simultaneously obtain spectra from multiple galaxies. This instrument can analyze the light from galaxies to determine their chemical composition, temperature, density, and redshift. This instrument is crucial for studying the detailed properties of galaxies and understanding their evolution over time. The NIR SPEC operates in the near-infrared, which is ideal for observing distant galaxies. By dividing the incoming light into its wavelengths, the instrument creates a detailed fingerprint of each galaxy, revealing its unique characteristics. The NIRCam, or near-infrared camera, has a different but complementary function. It takes high-resolution images of galaxies, allowing astronomers to study their structure and morphology. The camera is especially effective at observing faint, distant objects, making it indispensable for analyzing and identifying galaxies with high redshift. The wide field of view of the NIRCam allows capturing large areas of the sky in one image. This capability is fundamental for studies such as DD 2750 and GO 1433, where astronomers need to observe many galaxies simultaneously. By combining detailed spectra with high-resolution images, scientists can build a complete picture of these ancient galaxies. So, what did the scientists actually see? These ancient galaxies are incredibly small compared to our Milky Way. They're less than a kilo in diameter, about 1,000 times smaller than our Milky Way. Despite their tiny size, they're full of activity typical of young galaxies forming in the early universe. Some of them even present complex structures affected by gravitational lensing, a phenomenon in which a massive object in the foreground distorts the light of an object in the background, allowing us to see them in greater detail than would otherwise be possible. But why are these size differences so important? It is precisely the small size of these galaxies that suggests they are in the early stages of evolution. In the young universe, galaxies were still forming and merging, which led to intense star formation periods. These compact galaxies are like snapshots of the early universe that show us how they begin life and grow over time. What are these galaxies like? Sears 43833, for example, looks like a compact, bright object with hints of structure indicating regions of intense star formation. Sears 16943, although smaller, also shows signs of active star formation. In contrast, MAX 0647DJD shows a more complex morphology due to lens effects and shows multiple images of the same galaxy. However, it is the understanding of the light from these galaxies that is key to unlocking their secrets. This is where the spectral energy distribution, or SED, comes into play. The SED represents the range of energy emitted by a galaxy in different wavelengths, from ultraviolet to infrared. By studying the SED, astronomers can infer various physical properties of a galaxy, such as its age, mass, and star formation rate. We use the NURC and NURCam data from the JWST to create the SED. Then, we can model it using software that simulates different scenarios of galaxy formation and evolution. By adjusting the observed data to these models, we can estimate the stellar mass of the galaxy, its star formation history, and other important parameters. The SEDs of these galaxies indicate a relatively young stellar population, with intense star formation that occurred less than 100 million years ago. A detailed analysis of these SEDs helps us reconstruct the life history of these ancient galaxies, as we have already mentioned. The light from these distant galaxies contains a large amount of information, especially in the form of emission lines. Emission lines are bright lines that appear at specific wavelengths of the spectrum and are produced when elements in the galactic gas are energized and emit light. Each element produces a unique set of lines, much like a fingerprint, allowing us to determine the chemical composition of the galaxy. In addition to identifying the elements, the emission lines also reveal the physical properties of the gas and stars of the galaxy gases and stars of the galaxy. By analyzing the intensity and ratio of these lines, astronomers can estimate the star formation rate, which shows how many new stars are being born in the galaxy. For example, a strong Hal alpha emission line indicates a high star formation rate, indicating that the galaxy is actively producing new stars. Emission lines also help determine the oxygen content of the galaxy, which is an indirect indicator of its overall metallicity. This tells us how many generations of stars have existed, enriching the galaxy with heavier elements over time. Understanding these properties helps compile the history of the galaxy and determine its evolutionary stage. One of the most intriguing characteristics observed in these distant galaxies is the damped Lyman alpha, or DLA. But what exactly is a DLA? Simply put, the DLA is a broad absorption line in a galaxy's spectrum caused by the presence of large amounts of neutral hydrogen gas. This absorption line is much broader than normal lines, indicating a significant amount of gas. DLAs are important because they allow us to directly measure the amount of neutral hydrogen in the early universe. This information helps us understand how galaxies acquire the gas that fuels star formation and how they evolve. By studying the DLAs, we can learn about the conditions of the universe when these galaxies formed. The detection of DLAs in these galaxies involves analyzing their spectra for broad absorption features. This process allows us to quantify the amount of gas present and understand the environment surrounding young galaxies. The presence of DLAs in these galaxies tells us that they are rich in neutral hydrogen, which is crucial for star formation. It also provides information about the intergalactic medium, the space between galaxies, and its role in galaxy formation. By comparing the characteristics of the DLAs with different galaxies, we can build a more complete picture of the early universe. The discovery of these ancient galaxies offers a unique opportunity to compare them with other known superluminous galaxies. Unlike their more evolved counterparts, these newly discovered galaxies have distinctive characteristics that set them apart. What makes these new discoveries special is the unusual amount of dense gas surrounding them. This gas, composed mainly of hydrogen and helium, is one of the first elements that existed in the universe. The presence of such dense gas is unusual, as it indicates that these galaxies are in the early stages of their evolution. This dense gas likely feeds the formation of new stars, playing a key role in their evolution. Another unique characteristic of these galaxies is their low metal content. In astronomy, metallicity refers to the abundance of elements heavier than hydrogen and helium in a galaxy. The low metallicity also confirms that these galaxies have not gone through many cycles of stellar formation, which means that they have fewer heavy elements and that they are in the early stages of their evolution. So they are an ideal laboratory to study the initial stages of the formation of galaxies and their evolution. This information will help us reconstruct the sequence of events that led to galaxy formation in the early universe. These discoveries also fit into the broader context of understanding the universe's history. During the period known as the era of reionization, the universe went from opaque to being transparent. The galaxies discovered by the JWST are among the first to contribute to the reionization process by ionizing gas around them. The next steps involve creating large statistical samples of galaxies to estimate in detail the prevalence and brightness of their characteristics. The researchers will continue studying where the gas is, how much is near the center of the galaxies, and whether it is primordial or already contains heavier elements. Meanwhile, we will await new results and discoveries, which we will not hesitate to communicate to you. In the midst of the silent expansion of our solar system lies a world of profound mystery and rugged beauty. Mars, with its purple dunes and ancient valleys, tells of its tempting past. A planet where sunsets tinge the sky blue, where imposing dust devils roam the arid lands, and where the remains of water currents silently tell the story of times past. Here, among the red dust, is the enigmatic brain terrain, a geological wonder that defies explanation. Its intricate patterns, reminiscent of the complex folds of the human brain, remain one of the most challenging mysteries. What forces could have created these enigmatic formations? Are they the key to unlocking the secrets of Mars's past climate? As the sun dips below the horizon, the Martian sky transforms, casting blue light over the alien landscape. The scars of ancient rivers and the cracks of dry mud tell the story of an era in which water flowed freely through Mars, when the planet experienced the change of seasons, and when this world could have been more similar to Earth than we could have imagined. However, despite all its wonders, Mars is a clear reminder of its alien nature. Today we will travel to Mars, a world of beauty and mystery. A planet that holds the we will travel to Mars, a world of beauty and mystery. A planet that holds the keys to our past and the promise of our future. Join us to explore the mysteries of the good old red planet. Under the purple skies of Mars lies a canvas of geological mysteries, among which is the brain terrain. These complex patterns, reminiscent of the cerebral cortex, extend across the Martian mid-latitudes. Its origin is shrouded in mystery. What processes could have created such complex patterns? Scientists suggest that sublimation, the direct conversion of ice into vapor, plays a key role here. Although the exact process remains a mystery, it is very likely that the interaction between the underground ice and the thin Martian atmosphere forms the intricate patterns. But Mars is not a quiet world. It breathes and moves. The dust devils, those imposing columns of dust that rise kilometers into the rarefied atmosphere, are not only a spectacle of nature, but also the architects of the Martian surface. The bare landscapes they crisscross leave behind dark traces that testify to their passage. These ethereal giants, born from the interaction of heat and wind, reach more than 2 kilometers in height and are larger and more spectacular than their terrestrial counterparts. Then, as the Martian day fades, the sky transforms, and a Martian sunset bathes the landscape with an ethereal blue light that contrasts sharply with the familiar red and orange tones of the day. This phenomenon is due to the unique interaction of sunlight with the atmosphere of the red planet, filled with particles of iron dust, which, when passing through the red part of the visible spectrum of sunlight, is scattered by the dust particles, leaving only a fascinating blue glow. Although this scattered light tinges the sky red at sunset, and at night it transforms into blue tones, the mysteries of the Martian atmosphere do not end there. They end there. The interesting phenomenon of the green glow of Mars, recently captured by NASA's Odyssey orbiter, offers a vision of the unique characteristics of the Martian atmosphere. This glow, observed from orbit, results from atmospheric processes common throughout the solar system, but which manifest differently on each planet due to variations in the composition and density of the atmosphere. During the day, sunlight interacts with the Martian atmosphere, breaking down CO2 molecules through a process known as photodissociation. This releases individual atoms that, when reaching the night side of the planet, recombine into different molecules while emitting light. On Earth, this phenomenon produces a whole spectrum of colors, but on Mars the predominant color is green. This green glow is mainly due to the recombination of CO2 molecules in the upper atmosphere, an altitude of between 25 and 90 miles. Interesting studies have revealed an additional glow at lower altitudes, resulting from the recombination of oxygen atoms. This secondary glow, visible during the Martian summer, is concentrated in the polar regions where atmospheric currents converge. The intensity of this glow varies with the time of year, alternating between the northern and southern hemispheres. The thinness of the Martian atmosphere compared to Earth's allows these luminous phenomena to be observed and studied more directly. It has also made it possible to detect other emissions, such as those of nitrogen oxide in the ultraviolet spectrum, which further enriches our knowledge about the composition and behavior of the Martian atmosphere. These atmospheric studies not only shed light on the processes that shape the Martian environment, but also provide valuable information about the planet's past in present climatic conditions. Speaking of it, the Martian landscape, with its vast deserts and imposing volcanoes, contains a large number of clues about the planet's climatic past, among them signs of seasonal changes that have molded the surface for millennia. The presence of characteristics like the mud cracks discovered by the Curiosity rover that keep a surprising resemblance with similar objects on the Earth suggests the presence of liquid water in the past of the planet. In particular, it is believed that the mud cracks were formed over many Martian seasons, indicating a cycle of humid and dry periods that Mars experienced long ago. More evidence of the dynamic climate of Mars can be found in the remains of ancient glaciers in the planet's middle latitudes. These fossilized features printed in the Martian terrain speak of an epoch in which water ice slid across the planet's surface, excavating furrows and transporting sedimentary rocks. These glaciers, like their terrestrial counterparts, mold the terrain, leaving behind traces of their presence in the form of seas and excavated valleys. This activity suggests that Mars has undergone significant climatic changes, perhaps similar to the glacial and interglacial periods observed on Earth. The presence of sulfates in the mud cracks adds another layer to our understanding of the history of water on Mars. The mud cracks, like the ones that are found on the Earth, are formed by the drying of sedimentary rocks, what indicates the presence of stagnant water that evaporates periodically, leaving behind these prominent patterns or sinking under the surface. The detection of sulfates in these formations indicates that the water interacted with the Martian soil, giving rise to the deposit of minerals. The different levels of these sulfates, combined with the pattern of the mud cracks, paint a picture of a planet in which water levels rose and fell, creating conditions conducive to chemical reactions that could even sustain the precursors of life. Clearly, the search for water on Mars constitutes a key aspect to understanding the climate, the geological history, and the potential for habitable life on the planet. The recent discoveries have shed light on the presence of water in diverse forms and places on Mars, significantly changing our understanding of the red planet. On Mars, there are many geological features that indicate the presence of water in the past. The discovery of ancient lacustrine beds, fluvial valleys, and drainage channels indicates that at some point water flowed freely across the planet's surface. These characteristics suggest that Mars once had a warmer and more humid climate, capable of supporting liquid water on its surface. The presence of sedimentary layers and mineral deposits in these ancient lakes and fluvial valleys further reinforces the idea of prolonged hydric activity that could have lasted thousands or even millions of years. One of the most revolutionary discoveries is the finding of water ice near the Martian equator. Traditionally, it was thought that ice was only found in the polar regions of Mars, where it is visible on the surface. It is visible on the surface. However, studies with radar and analyses have revealed deposits of ice beneath the surface in lower latitudes, even near the equator. This refutes previous ideas about the climate of Mars and suggests that water ice is much more widespread throughout the planet than previously thought. The implications of the equatorial ice extend to the climatic history of Mars and its potential habitability. The deposits of equatorial ice indicate a more complex hydrological cycle on Mars than previously thought. This could mean that, in the past, Mars had a climate more similar to the one of the Earth, with a water cycle between the atmosphere and the surface. However, this presence does not at all guarantee the possibility that in the past there existed adequate conditions for life on Mars, much less in the present. Water is a key component of life, but such a contrasting climatic change does not offer many possibilities for a long process of development of any form of life. The search for biosignatures like special minerals, organic molecules, or erosion patterns that can indicate biological activity in the past continues, although conclusive proof of life on Mars has not been found yet. The presence of water in diverse forms continues to maintain a minimal possibility. Even so, these ice deposits could serve as a valuable resource for the future exploration and human colonization of the planet, providing water to drink, for agriculture, and for the production of fuel. If we observe more closely the mineralogical landscape of Mars, we see that a marked contrast with the rich diversity that is found on the Earth. In our planet, about 6,000 different minerals have been discovered, what gives testimony of the dynamic geological processes of the Earth and of the complex interaction between the biosphere and the geosphere. These minerals have not only been formed by abiotic processes, but have also been significantly influenced by the presence of life, which has contributed to the diversity of the minerals through diverse biochemical interactions. In comparison, after 5 decades of investigation, only 161 minerals have been identified on the Martian surface. This divergence in mineral diversity is not only a numerical difference, but it tells us a lot about the differences in the geological activity and history of the two planets. The scarcity of minerals on Mars has profound implications for our understanding and its potential to support life. The diversity of minerals in a planetary body is usually a reflection of its geological and environmental dynamism. On the Earth, the plate tectonics, the availability of water, and the atmospheric processes contribute to the ample range of physical and chemical conditions that are so essential for the origin and the maintenance of the life. Complex organic molecules, including the precursors of DNA, usually require diverse chemical environments and catalysts. Therefore, the limited mineral diversity of Mars poses some questions about the habitability of the planet as a whole. The scarcity of diverse minerals on Mars also indicates that the planet may have had a more monotonous geological history compared to Earth. However, is it as calm and peaceful as it seems? Recent studies of the internal structure of Mars have led to interesting discoveries, particularly through the analysis of seismic data. The InSight mission played a key role in this discovery before its completion, when detecting what is believed to be the biggest earthquake ever registered on Mars. This earthquake, which lasted about 6 hours, did not conform to the typical profile of a meteorite impact, since it did not leave any crater, suggesting that it originated in the planet's depths. The magnitude of the earthquake, which was 47 on the Richter scale, points to significant geological activity beneath the surface. Unlike Earth, Mars lacks tectonic plates, which poses intriguing questions about the mechanisms that cause these earthquakes. The absence of tectonic plates suggests that the Martian earthquakes can be related with internal tensions or other geological processes that we still do not understand completely. Volcanic activity on Mars, both recent and ancient, has left indelible marks on its surface. Recent studies have found at least 40 different volcanic events, some of which occurred only a few million years ago. In addition, the discovery of unusual polygonal structures under the surface, found by a ground-penetrating radar of the Chinese rover Che, indicates a history of contraction and thermal expansion and speaks of these structures, whose size varies between a few centimeters and several meters, have been found at depths of about 30 meters. It is evident that drastic climate change or some cataclysm has caused these deposits to be at such a depth under the surface of the planet. The region known as Noctis Labyrinthus, with its vast network of valleys and canyons, is further proof of the volcanic past of Mars. Located near the Tharsis volcanic plateau, where the largest volcano in the solar system, Olympus Mons, is located, this region demonstrates the dramatic impact of volcanism on the Martian landscape. A video simulation provided by ESA shows how the stretching and flexing impacted Olympus Mons. This region demonstrates the dramatic impact of volcanism on the Martian landscape. A video simulation provided by the ESA shows how the stretching and flexing of the Martian crust in this region, which led to the formation of deep valleys and canyons, proves the planet's active geological past. The release of water during volcanic eruptions may explain the presence of ancient river valleys and lakes, allowing us to glimpse an era when Mars may have been more like Earth, with a warmer, more humid climate. Understanding the planet's volcanic history not only sheds light on its past climate and potential for harboring life, but also helps in future research, as regions with volcanic activity in the past may contain clues about the habitability of the planet to inhabit and the availability of vital resources. Speaking of habitability, it is impossible not to mention the recent successes in the production of oxygen on Mars. The Mars Oxygen In Situ Resource Utilization Experiment, or MOXIE, was an achievement of space technology that managed to produce oxygen from the carbon dioxide in the Martian atmosphere. Installed aboard NASA's Perseverance rover, MOXIE operates efficiently in various Martian conditions, both day and night and in different climatic states. Its ability to convert CO2 into oxygen through the solid oxide electrolysis process is a significant technological achievement. By heating the Martian atmosphere to 800 degrees Celsius, MOXIE decomposes CO2 into oxygen and carbon monoxide and then recombines the oxygen ions into breathable O2. This process has been shown to achieve the required oxygen production and purity, despite design trade-offs due to mass, power, volume, and cost limitations associated with space missions. MOXIE's success has profound implications for the future of human exploration and the potential colonization of Mars. The ability to produce oxygen on Mars paves the way for a sustainable human presence, reducing dependence on Earth for critical resources. The study concludes that a large-scale version of MOXIE could generate tens of tons of oxygen, essential not only for astronaut life support, but also as a critical component of rocket fuel. Such a capability would significantly reduce the logistical and financial burden of transporting oxygen from Earth to Mars, which would otherwise require launching hundreds of tons of material into space at an exorbitant cost. By providing a reliable supply of oxygen, systems like MOXIE could support longer missions, larger crews, and even permanent settlements on Mars. In addition, the technology can be adapted to produce other necessary resources, such as water and fuel, which is a significant step towards realizing the dream of a self-sufficient human presence on the red planet. Speaking of the Perseverance rover, we must also mention its Ingenuity helicopter, which has far exceeded the original parameters of its mission on the Martian surface. Built only for a brief technology demonstration, Ingenuity was only supposed to perform 3 flights in 30 days, but far exceeded those expectations by performing 72 missions for more than 1,000 Martian days, demonstrating its resilience and adaptability to the harsh Martian environment. This achievement was not only an important milestone in the aerial exploration of planets, but also laid the foundation for future missions. Ingenuity's journey was not without challenges, as it encountered and overcame numerous technical problems, including communication interruptions and unexpected landings. Despite these challenges, Ingenuity continued to push the limits of what was possible and even set a new range record on one of its flights. The vehicle's ability to survive and operate despite Martian dust storms, extreme temperatures, and even sensor failure demonstrates the reliability of its design and the team's careful planning. However, the mission ended unexpectedly when an important part of the blade of one of Ingenuity's rotors broke, making it impossible to continue with the flights. This incident marked the official end of the Ingenuity Mars mission. The helicopter's last flight took place in January 2024. However, the completion of the Ingenuity mission does not detract from its extraordinary achievements and the valuable data it provided. NASA has already begun to apply the lessons learned from operating aircraft in extraterrestrial environments to upcoming missions, including the Dragonfly mission to Titan, Saturn's largest moon. Ingenuity's success has opened the door to a more ambitious use of aircraft for tasks such as sample recovery, which could significantly increase the efficiency and scope of exploration of other planets. During its long stay on the red planet, the Perseverance rover has accumulated a considerable amount of samples of Martian rock materials. However, it should be noted that the undertaking of returning samples from Mars to Earth is both the pinnacle of scientific endeavor and the greatest logistical challenge. The financial implications are staggering. According to recent estimates, costs could exceed those of the most expensive space missions, such as the James Webb Space Telescope, which total $11 billion. The complexity of extracting samples from a Martian surface and transporting them back to Earth involves multiple spacecraft and precise robotic operations. This task requires not only precision engineering and unprecedented navigation solutions, but also significant financial investments, raising questions about budgetary allocation and priorities in space exploration when it comes to prioritizing space exploration. Humanity faces another unresolved challenge: the ongoing debate about international cooperation in precision engineering and unprecedented navigation solutions, but also a significant financial outlay, raising questions about budgetary allocation and priorities in space exploration. When setting priorities in space exploration, humanity faces another unresolved challenge. The ongoing debate about international cooperation in the exploration of Mars is multifaceted and involves political, scientific, and logistical considerations. On the one hand, cooperation can pool resources, share risks, and increase the scientific yield of missions through the diversity of expertise. On the other hand, comparing the successes of collaborative initiatives, such as the International Space Station, against the backdrop of some international limitations highlights the contradiction between the ideal of a united human effort in space exploration and the reality of international relations on Earth. Another test, but not the last, on our way is that, as Mars becomes a center of exploration and possible colonization, the problem of space debris is becoming increasingly important. The accumulation of debris in Martian orbit can pose a hazard to spacecraft, impede navigation, and endanger missions. This problem is not only theoretical. The proliferation of debris around Earth has already created an urgent need to develop sophisticated tracking and avoidance systems. In turn, solving this problem on Mars will require proactive measures to prevent the accumulation of debris and possibly the development of debris reduction and removal technologies to ensure the safety and sustainability of future missions. The colonization of Mars, which was once the stuff of science fiction, is increasingly entering the realm of the possible thanks to technological advances and scientific discoveries. The successful demonstration of in situ resource utilization through experiments like MOXIE, the potential of using local materials for construction, and advances in life support systems are gradually laying the foundations for a sustainable human presence on Mars. However, the vision of colonization goes beyond just technological challenges and includes ethical, social, and environmental considerations. The responsibility of extending humanity's footprint to another planet raises questions about how we manage Earth and the extent to which we can apply these lessons to the new world. The future of Mars exploration is promising and full of challenges. As we stand on the threshold of these efforts, the collective wisdom, ingenuity, and cooperative spirit of the global community will play a key role in overcoming these challenges and making the dream of expanding humanity's presence beyond Earth a reality. Music. What if the colors we see in the night sky are only the beginning of a story yet untold? Our documentary invites you on a journey of discovery, where each chapter unveils the hidden narratives of distant worlds that challenge what we thought we knew about our universe. First, we dive into the blue depths of Neptune, revealing its true colors, a world far beyond our own, where fierce winds and skies tell stories of ice and gas. What mysteries does this distant giant hold within its Killian tones? Next, we venture to the enigmatic Saturn, where at its North Pole, a geometric wonder, the hexagonal storm, defies all explanation. What forces of nature sculpt this strange phenomenon? Can we reveal the secrets of the? Our odyssey continues in search of the latest real images of Uranus, this elusive ice giant shrouded in mystery that reveals new truths through modern exploration. What will we discover in the hidden details of its atmosphere and rings? Finally, we travel with Chandrayaan-3 to our celestial neighbor, the Moon. Here, in the silence of the lunar surface, the mission discovers images never before seen by the human eye. What did Chandrayaan-3 witness on the Moon? What secrets are hidden in the dust and craters of our closest companion in space? Join us as we travel the cosmos in search of answers and marvel at the beauty of the universe. This is not just a journey through space. It is an exploration of the unknown, a search for knowledge, and a tribute to the infinite curiosity of the human spirit. Welcome to our documentary series, where the mysteries of the universe are revealed before your very eyes. In the vastness of our solar system, beyond the asteroid belt and gas giants, lies a world shrouded in mystery. Neptune, the eighth planet from our Sun, is a distant ice giant that has captivated our imagination for decades. We have imagined it as a dark blue sphere on the edge of our cosmic neighborhood. But what if the vision of this distant world was an illusion? This mysterious planet, named after the Roman god of the sea, has hidden its true colors from us, shrouded in a veil of deep blue. Neptune has been the subject of many stories and scientific investigations, but recent discoveries have eliminated this blue facade, revealing a reality far more complex and fascinating than we have imagined for years. Our telescopes have been pointed towards this distant giant, capturing its essence in pixels and data. However, what we saw was not the reality of the planet, but a reflection of our own technological and perceptive limitations. The deep blue color that we associated with Neptune was actually the result of our own interpretations and enhancements, a story that we created and believed without knowing it. Today, we invite you to explore Neptune like never before, to delve into its true colors, to understand its dynamic atmosphere, and to unravel the secrets of its moons and rings. For centuries, Neptune was like a dark blue world whose color reflected its cold and distant nature in the solar system. This representation, deeply rooted in our collective consciousness, has become the cornerstone of our understanding of this ice giant. But what if this image were a reflection of our perceptions rather than the planet's true appearance? Its true appearance. The color of Neptune is a story of scientific evolution and the search for truth. It begins with the two Voyager probes launched by NASA in 1977 and sent to the confines of the solar system. These took the first close-up images of Neptune, painting a picture of the planet bathed in a stunning blue color. However, these images were not a direct window to the true color of Neptune, but interpretations resulting from processing the data through the prism of human knowledge and the technological capabilities of the time. The intense blue color we saw was the result of enhancements made by scientists to highlight certain characteristics of the planet. This story began to unfold with the arrival of more advanced telescopes, such as the Hubble Space Telescope and the Very Large Telescope. These instruments, equipped with state-of-the-art technology, allowed astronomers to see the planet's true color again. The results of this study were surprising. The new images reveal that the color of Neptune was not the previous deep blue, but a more muted and varied tone. This discovery was not only aesthetic, but a fundamental change in our understanding of the planet. The reason for this color error lies in the way we process and interpret astronomical data. The colors in space images are often enhanced or altered to emphasize certain features or to make them more distinguishable to the human eye. In the case of Neptune, these enhancements over time have led to a collective opinion about its deep blue color. What led to this discovery? The key lies in a meticulous study entitled Modeling the Seasonal Cycle of Color and Magnitude of Uranus in Comparison with Neptune. This study, led by Patrick G.J. Irwin of the University of Oxford, along with a team of experts, set out to unravel the mysteries of seasonal color changes. However, its journey will inadvertently shed light on Neptune's true colors, refuting ingrained beliefs. The team carefully analyzed a large amount of data obtained from the L Observatory for 6 decades. This data, complemented by observations from the Hubble Space Telescope, produced a detailed image of the average color and photometric magnitude of Uranus, revealing the complex interaction of its seasonal changes. One of the most important aspects of this study was the focus on the reflectivity of Uranus and the abundance of methane. The researchers unraveled a complex relationship between the lower methane content in the polar latitudes and the different reflectivity of aerosol particles. It is believed that this complex interaction of elements in Uranus' atmosphere is influenced by the presence of methane ice particles, adding a new level of complexity to our understanding. In parallel, the study allowed a fascinating comparison to Neptune. Contrary to popular belief, the difference in blue tones between Neptune and Uranus was less pronounced. This discovery was the result of a critical reevaluation of the color of Neptune, which belied the image of deep blue that had taken root in our minds. The methodology used by the team was a combination of quantitative analysis, atmospheric modeling, and advanced spectroscopic observations. They converted the measured reflectance spectra into radial spectra and then into tri-stimulus values. This process mimicked the visible colors of the planets as perceived by the human eye. To bridge the gap between raw data and our visual interpretation, the use of advanced telescopes, such as the Hubble and the Very Large Telescope, played an important role. These technological wonders allowed the team to review and re-examine the true colors of Uranus and, by extension, Neptune with unprecedented precision. As we delve into the mysteries of Neptune Tenno, we find ourselves in the midst of a whirlwind of atmospheric activity that contrasts with the relative calm of its stellar neighbor, Uranus. Neptune's atmosphere, a turbulent and dynamic formation, is home to some of the most extreme meteorological phenomena in our solar system. One of the most striking features of Neptune's atmosphere is the presence of colossal storms, the most famous of which was the Great Dark Spot discovered by the Voyager spacecraft in 1989. This huge storm, similar to the Great Red Spot of Jupiter, is a testament to the turbulent nature of the planet. The Great Dark Spot, a giant rotating storm, is a window into Neptune's intense atmospheric dynamics. These storms are caused by the strongest winds in the solar system, which reach speeds of up to 1,300 miles per hour. However, to this day, the magnitude of these winds remains a mystery to scientists, raising questions about their origin and the energy sources that drive them. In contrast, its neighbor Uranus is an image of tranquility. Its atmosphere, although composed of hydrogen, helium, and methane, does not present the same violent storms or extreme winds as Neptune. The difference in atmospheric activity between these two ice giants is one of the many mysteries of our solar system. Another intriguing aspect of Neptune's atmosphere is the presence of unusual hot spots, where temperatures can reach 750 degrees Kelvin. These hot spots represent a paradox, since they exist on a planet so far from the Sun. The origin of this heat remains a mystery, but theories suggest it could be caused by internal processes such as auroras or magnetic reconnection in the plasma layers. The origin of these hot spots and the extreme climatic conditions of Neptune are the subject of ongoing research. They force us to look for new answers to questions about planetary atmospheres and point to complex internal processes that are not yet understood. As we leave Neptune's turbulent atmosphere, we enter a realm of celestial harmony where the moons and rings revolve around this ice giant. By turning our gaze towards Triton, Neptune's largest and most intriguing moon, we discover a world of seasonal changes and atmospheric mysteries. Triton, a unique moon with a retrograde orbit, was the last solid object visited by the Voyager spacecraft during its historic journey through the outer solar system. Due to its retrograde orbit, which indicates that it was captured by Neptune's gravity, Triton stands out among the moons in our solar system. Its surface, covered with nitrogen ice, is geologically young and active, with dark streaks indicating the presence of geysers that expel nitrogen gas. Triton's thin atmosphere, whose thickness varies with the seasons, is a fascinating study in extraterrestrial meteorology. Observations made with the Large Telescope of the European Southern Observatory with its Large Telescope have revealed that Triton's southern hemisphere is in full summer. This distant moon, despite its relative distance from the Sun, is experiencing significant atmospheric changes. The summer sun's heat causes the thin layer of frozen nitrogen, methane, and carbon monoxide on Triton's surface to sublimate and turn into gas. This process causes the icy atmosphere to thicken as the season progresses in Neptune's orbit, 165 times longer than Earth's. The season on Triton lasted more than 40 years, and the southern summer solstice occurred in 2000. The discovery of carbon monoxide in Triton's atmosphere, as well as the confirmation of the presence of methane, was a significant advance in our understanding of this moon. The presence of these gases, especially the enrichment of ice with carbon monoxide in the upper layer of the surface, feeds the atmosphere, and determines its seasonal dynamics. These findings required a revision of Triton's climate and atmospheric models. The complex interaction between nitrogen, methane, and carbon monoxide not only determines atmospheric conditions, but also provides information about the Moon's geological and climatic history. But Triton is not alone. The planet is accompanied by a retinue of smaller moons, each contributing to our understanding of this distant world. These moons also show seasonal changes and provide information about the complex gravitational interactions and environmental conditions around Neptune. When we turn our gaze from the moons to Neptune's rings, we find another aspect of the mysterious nature of this planet. Neptune's rings, formed by a mixture of dust and ice particles, are opaque but fascinating and testify to the dynamic history of the planet. Scientists believe they are remnants of moons that were destroyed by collisions and torn apart by Neptune's gravity. The composition and characteristics of these rings are closely related to Neptune's true color and atmospheric phenomena. The subtle tone of the rings, which is affected by the dispersion of light in the atmosphere of Neptune, adds another layer to the color palette of the planet. The rings, reflecting and refracting sunlight, create Neptune's overall appearance as seen from afar. In 2022, the James Webb Telescope captured the clearest image of this distant planet's rings in 30 years. Photographed with unprecedented clarity, these rings have changed our thinking about this distant planet. The most striking thing about the new Webb image is the clear view of Neptune's rings. Some of these faint, dusty rings have not been detected since the historic Voyager flyby in 1989. The Webb Telescope, with its enhanced capabilities, has refocused on these elusive rings. The rings of Neptune are formed by several bands of bright, narrow dust, as well as fainter ones. The infrared images from the Webb Telescope have put these rings in a new light, revealing characteristics that were previously hidden in the darkness of space. It is the first time that these rings have been seen in the infrared spectrum, providing new knowledge of their composition and behavior. The rings of Neptune, like the planet itself, are characterized by a unique composition, different from that of the gas giants Jupiter and Saturn. Neptune is an ice giant rich in elements heavier than hydrogen and helium. This composition is also reflected in the characteristic blue color, invisible in wavelengths caused by a small amount of methane gas in the infrared images taken by the near-infrared camera Webb camera. Neptune does not appear blue, in contrast to the darkened appearance that would be expected due to the absorption of light by methane in the infrared images taken by the Space Telescope. Neptune appears as a luminous and bright white sphere. This absorption also affects the appearance of the rings of Neptune, as they reflect and refract the light that travels through the planet's atmosphere. This unexpected brightness in the infrared results from a unique interaction between the planet's atmosphere and light. While methane gas absorbs red and infrared light, high-altitude clouds in Neptune's atmosphere reflect sunlight before it is absorbed. In the infrared spectrum, methane ice clouds appear as bright streaks and spots that cast a ghostly glow on the planet. By the way, you may wonder why Triton looks like a dazzling point of light adorned with bright spikes, contrasting with the fainter image of Neptune. These diffraction spike patterns are a feature of the imaging telescope. They are not physical structures, but optical artifacts created by the telescope's design. The light from Triton that passes through the mirrors and structure of the telescope is diffracted, giving rise to these striking peaks emitted by the moon. In simple terms, diffraction is what happens when a wave, such as light, travels through a small opening or around the edge of an object. Imagine light as water waves flowing through a narrow slit in a wall. When the waves pass through the slit, they deviate in different directions instead of going straight. This propagation of waves after passing through a hole or around an edge is diffraction. In the context of the James Webb Space Telescope and its images, diffraction causes peaks to arise due to the arrangement of the mirrors and structure of the telescope. When light from a bright object, such as a star or Triton in the images of Neptune, enters the telescope, it is slightly deflected by the edges of the mirrors and other parts of the telescope. As a result of this deviation, The light is scattered and forms the star-shaped peaks that we see in the images. The study of the rings of Neptune, especially in the infrared, provides valuable information about the atmospheric conditions and internal composition of the planet. The interaction of the rings with the atmosphere of Neptune, in particular with the methane ice clouds, provides information on the climatic and environmental processes of the planet. The bright equatorial band that surrounds the planet gives clues to global atmospheric circulation, a key factor in the planet's winds and storms. The atmosphere, which descends and heats up near the equator, shines more intensely in the infrared than the colder gases that surround it. As we conclude our journey through the mysterious world of Neptune, we reflect on the impact that these discoveries are having on the broader field of planetary science and the exploration of exoplanets. Neptune, once a distant blue dot, is now a testament to space exploration's power. The dynamic and constantly evolving discoveries about the true color of Neptune, its atmospheric phenomena, and the intricate details of its rings and moons go far beyond our solar system, providing a crucial example for understanding similar ice giants and exoplanets within the confines of our galaxy. The knowledge gained about Neptune will help astronomers decipher the mysteries of these distant worlds and enrich our knowledge of the universe as we continue to contemplate the cosmos. Neptune reminds us of the unlimited potential of discovery. Its example encourages us to continue searching, asking questions, and unraveling the mysteries of the universe. Saturn has captivated the human imagination from ancient times to modern astronomers. The Maori of New Zealand, separated by vast oceans, somehow knew that Saturn had rings. How the mystery deepens. Saturn has long been a symbol of the unknown and mysterious. Its iconic rings have been the subject of awe and speculation since Galileo's time. But what if we told you that these rings, as eternal as they seem, are actually a fleeting cosmic phenomenon that adds to the intrigue? A storm twice as wide as Earth with a mysterious hexagonal shape that breaks out at Saturn's North Pole. What forces could have created such a geometrically perfect formation? But the mysteries do not end there. Saturn's satellites, Titan and Enceladus, offer conditions that may harbor life. Lakes of liquid methane and geysers that launch water and organic matter into space make these satellites more than simple celestial bodies. They're potential homes for life. Join us to learn more about this enigmatic giant and its cosmic mysteries. Our journey begins with Galileo Galilei, the Italian astronomer who first pointed his telescope at Saturn in 1610. What he saw left him perplexed, a planet with something like ears. He did not realize he was seeing the edges of Saturn's magnificent rings, a characteristic that would baffle astronomers for centuries. Galileo's telescope was primitive by today's standards, and the true nature of Saturn's ears remained a mystery. It was not until 1655 when Christian Huygens, armed with a more advanced telescope, correctly identified them as a system of rings around the planet. Entering the modern era, we witnessed the Pioneer 11 mission, the first spacecraft to fly by Saturn in 1979. This mission provided us with the first close-up images of the planet and its rings, revealing intricate details that were previously inaccessible to terrestrial telescopes. But it was the Cassini mission that truly revealed Saturn in all its splendor. Launched in 1997 and arrived at Saturn in 2004, Cassini spent 13 years studying the planet, its rings and its satellites, from the discovery of columns of water ice in Enceladus to the capture of the ethereal beauty of a hexagonal storm in the North Pole of Saturn. Cassini revolutionized our understanding of this distant world, and here is an interesting fact. Long before the arrival of telescopes, the Maori of New Zealand had myths that described Saturn with a pararo, or belt, around it. How they knew it remains a matter of debate, but, as we will see later, Saturn hides more than one mystery. What do you think could have created a hexagonal storm with a surface larger than Earth itself? Saturn is home to a geometric enigma at its North Pole, a six-sided storm that has baffled scientists for decades. This six-sided wonder is not just a superficial feature, but a deep and lasting mystery that challenges the foundations of fluid dynamics and planetary atmospheres. The hexagon was first discovered in 1981 by the Voyager spacecraft, but it was not until the Cassini mission, which orbited Saturn between 2004 and 2017, that we could see this cosmic spectacle firsthand. Cassini's high-resolution images showed a symmetrical jet stream surrounding the hurricane-like vortex at the hexagon's center. Unlike Earth's chaotic weather systems, Saturn's hexagon is a masterpiece of geometric precision. So, what causes this hexagonal storm? Researchers at Harvard University have developed a 3D model suggesting that deep thermal convection in Saturn's outer layers may be responsible. This model shows that the storm could extend thousands of kilometers into Saturn's atmosphere, far beyond what we can observe. Interestingly, scientists have been able to reproduce the hexagonal pattern in a laboratory environment. Although these experiments do not capture all the nuances of Saturn's complex atmosphere, they provide a glimpse of extraterrestrial phenomena. Saturn's hexagonal vortex contrasts sharply with Earth's polar vortex, which is irregular and less stable. This difference raises questions about the fundamental properties that distinguish the atmospheres of gas giants from the planets of the terrestrial group. The hexagon's longevity is another mystery, as it has been observed for at least 4 decades and possibly much longer. This constant characteristic suggests that whatever feeds the hexagon is not a temporary phenomenon, but a stable, perhaps even permanent, aspect of Saturn's internal dynamics. Let us now turn our attention from the mystery of the hexagon to another wonder of Saturn. Saturn's rings are more than just a celestial jewel. They're dynamic systems in constant change that interest both astronomers and the general public. But what are these rings made of, and why are they so ephemeral? Saturn's rings are mainly composed of water ice with a mixture of dust and rocky material. Their size varies from tiny particles to huge chunks the size of houses. These ice particles are not static, but are in constant motion under the influence of Saturn's gravity and the gravitational attraction of its satellites. The rings are divided into several subdivisions and gaps, each with its own unique characteristics. The most notable are the A, B, and C rings, separated by gaps such as the Cassini division, a 3,000-mile gap between the A and B rings. The origin of Saturn's rings has been the subject of debate. One popular theory suggests that they formed from the remains of a shattered moon. Another theory claims that they're the remains of material from the solar system's formation captured by Saturn's gravitational force. Recent research has also shown that the rings may be much younger than Saturn itself, perhaps around 400 million years old, based on the rate of dust contamination in Saturn's rings. They do not last forever, but are slowly disappearing due to a phenomenon known as ring rain, in which particles from the rings are drawn into Saturn's atmosphere. This process is accelerated by the bombardment of micrometeorites and interaction with Saturn's magnetic field. At the current rate, some scientists predict that Saturn's rings will disappear within 100 million years. The disappearance of the rings would not only change Saturn's appearance, but could also have consequences for its atmosphere and magnetic field. As we pause for a moment, we realize that even the most fascinating aspects of our universe are not immune to the inexorable forces of physics, doomed to disappear in the chronicles of eternity. Saturn, the ring giant of our solar system, is not only a celestial wonder, but also a cosmic playground containing some of the most intriguing satellites, 2 of which, Titan and Enceladus, have fascinated scientists and sparked debate about the possibility of life beyond Earth. Titan is a world shrouded in mystery. Its dense atmosphere is rich in organic compounds, and its surface has lakes and rivers of liquid methane. But what is truly surprising is the speed at which Titan moves away from Saturn, 100 times faster than previously thought, which is an astonishing 43 centimeters per year. This rapid drift suggests a dynamic and evolving relationship between Titan and Saturn. Could this drift affect Titan's internal dynamics and perhaps even its potential for life? An atmosphere rich in organic compounds, such as nitrogen and methane, and the possibility of an underground ocean make Titan a tempting target in the search for extraterrestrial life. But the question remains, What would life be like in an environment so radically different from Earth's? Let's remember Enceladus, another Saturn satellite very different from Titan. It is an icy world with a highly reflective surface that outshines any other body in the solar system. Enceladus takes the oceanic world concept to a new level. It not only has an underground ocean, but also expels it into space, where a probe can collect samples. This ocean contains most chemical ingredients necessary for life, including hot, mineral-rich water that gushes from hydrothermal vents. Hydrothermal vents can provide the conditions necessary for life as we know it on Earth. These sources teem with life forms that thrive in extreme conditions. Could Enceladus sources harbor similar, yet alien, life forms? Enceladus also contributes to Saturn's E-ring, a unique feature that further enriches the dynamic relationship between the Moon and its host planet. The icy particles of this ring open a window to the internal chemistry of the Moon, providing clues that could reveal its secrets. Titan and Enceladus are two moons orbiting the same planet, but with very different characteristics. Both present compelling arguments in favor of the possibility of life, which fuels our curiosity as we explore the possibilities of life on Saturn satellites. It is worth noting that our curiosity is not limited to telescopes and computer models. Upcoming missions aim to study these satellites up close and perhaps answer some of our most pressing questions. Meet Dragonfly, NASA's ambitious mission to Titan, scheduled for launch in the 2030s. This helicopter will fly over Titan's varied terrain, from dunes to impact craters. Dragonfly's main objective is to search for the basic components of life. It will analyze complex organic compounds in the atmosphere and on the surface, providing invaluable data on Titan's chemistry. Equipped with a suite of scientific instruments, Dragonfly seeks to understand the Moon's geological processes and their relation to its potential to harbor life. Could Titan's unique chemical composition and liquid methane cycles offer a different recipe for life? Although no missions are currently planned for Enceladus, its potential for life has made it an ideal candidate for future exploration. Scientists are proposing missions that could fly through Enceladus plumes and take samples directly from its underground ocean. Such a mission could analyze the plume's chemistry for signs of life or prebiotic chemistry. The presence of hydrothermal vents in the oceans of Enceladus and another layer of intrigue suggest an environment in which life could thrive despite the technical challenges. A mission to Enceladus could revolutionize our understanding of the potential for life in the solar system. It could provide direct evidence of the existence of extraterrestrial life, or, at least, clues about the conditions necessary for life to exist. Music. As we have mentioned, Saturn's rings are not eternal, as was once thought. Recent studies show that a process lasting hundreds of millions of years is causing these icy wonders to slowly fade. But how important is this to Saturn and its complex atmospheric dynamics? According to a study by the Japan Aerospace Exploration Agency, this material, mainly water, causes a decrease in electron density in Saturn's atmosphere. This phenomenon, known as ring rain, significantly affects Saturn's atmospheric conditions. The ring rain is not just a trickle, but a torrent that drags water in amounts equivalent to an Olympic swimming pool every half hour. The mystery is compounded by the relative youth of Saturn's rings, since, although Saturn is about 46 billion years old, data from NASA's Cassini mission suggests the rings may be only a few 100 million years old. This leads us to wonder, if Saturn's rings are so young, what catastrophic event could have led to their formation? Was it the destruction of a moon, or perhaps the capture of a passing comet? Cassini's Space Dust Analyzer has added another layer of complexity. For 13 years, it has collected 10,063 dust particles from outside the Saturn system. Surprisingly, the rings turned out to be quite clean, suggesting that they have not existed long enough to accumulate excess cosmic dust. This cleanliness raises the question, if the rings are young, why have they not collected more cosmic dust? The absence of cosmic dust in the rings challenges our understanding of their age and interaction with the broader cosmic environment. It is as if the rings were in a cosmic laboratory or in a clean room, isolated from the dust that permeates the rest of the solar system. As the rings deplete, Saturn's appearance will undergo a dramatic transformation. These rings have been the planet's hallmark, and their disappearance would not only change Saturn's appearance, but could also have unknown consequences for its atmosphere, even affecting the planet's albedo and heat retention. The loss of the rings could have a ripple effect on Saturn's atmosphere, potentially altering wind patterns and even affecting the planet's iconic storms. The full extent of these changes is still unknown, making them a topic of great scientific interest. Interestingly, the fate of Saturn's rings may be inextricably linked to that of its satellites. Some theories suggest that gravitational instability may have destroyed some of the satellites orbiting Saturn, providing enough material to form the rings. Saturn's rings and satellites are like companions in a cosmic dance, each affecting the other in subtle but significant ways. As we continue to study these celestial bodies, we can affirm Saturn's rings and satellites are like companions in a cosmic dance, each affecting the other in subtle but significant ways. As we continue to study these celestial bodies, we can state without a doubt that the fate of one can shed light on the mysteries of the other. In the vast theater of our solar system, where planets like Jupiter and Saturn often attract attention with their majestic rings and violent storms, there is a distant world shrouded in mystery and intrigue. This is Uranus, an enigmatic ice giant that often goes unnoticed, but hides secrets that could unlock some of the most enduring mysteries of the cosmos. Beyond the asteroid belt and between the orbits of Saturn and Neptune, Uranus travels as a cold and enigmatic ice giant that often goes unnoticed, but hides secrets that could unlock some of the cosmos' most enduring mysteries. Beyond the asteroid belt, nestled between the orbits of Saturn and Neptune, Uranus travels through the cold and dark corners of our solar system. It is a world that lives at a different pace, spinning on its side, a rarity that has long puzzled astronomers and given rise to countless theories. Discovered in 1781 by William Herschel, Uranus was the first planet discovered through a telescope, expanding the known limits of our solar system. For centuries, this distant world was nothing more than a point of light in our telescopes, a ghostly blue ball, distant and remote, guarding its secrets. But now, with the arrival of the James Webb Space Telescope, a new chapter opens in the exploration of Uranus. The JWST, with its unprecedented vision, uncovers the layers of this ice giant and reveals a world of incredible beauty and complexity. Let's travel together to this mysterious ice giant and learn about the latest discoveries made by the James Webb Space Telescope. In its quest to understand the universe, humanity has launched a sentinel into space, a marvel of engineering and a testament to our insatiable curiosity. This sentinel is the James Webb Space Telescope, the most advanced and powerful space telescope ever built, successor to the legendary Hubble Space Telescope. Equipped with a set of advanced instruments and a mirror of more than 62, the JWST is designed to observe the universe in a light invisible to the human eye, the infrared spectrum. This allows the telescope to pass through clouds of cosmic dust, discover distant galaxies, and study the atmospheres of exoplanets. The telescope's journey into space was quite a feat in itself. Launched on an Ariane 5 rocket, the JWST traveled to a point in space known as the second Lagrange point. Journey into space was quite a feat in itself. Launched on an Ariane 5 rocket, the JWST traveled to a point in space known as the second Lagrange point, or L2, 1 million kilometers from Earth. Here, in this stable orbit, the JWST can observe the universe with minimal interference from the Earth and the Sun. The capabilities of the JWST are not limited to observing the early universe or distant galaxies, but play a key role in unraveling the mysteries of our solar system. Its powerful instruments, such as the near-infrared camera CAM and the mid-infrared instrument MIRI, reveal new details about planets, moons, and other celestial bodies closer to us. Take Uranus as an example. In the past, our vision of this distant planet was limited to blurry images obtained with telescopes like Hubble. But now, thanks to the enhanced infrared capabilities of the JWST, we can see Uranus in a new light. The telescope's sensitive instruments allow us to observe its atmosphere, its weather patterns, and even its mysterious rings with unprecedented clarity. By analyzing the light from Uranus, the JWST can decipher the chemical composition of its atmosphere, revealing the presence of gases such as methane and hydrogen. This not only helps us understand the current state of Uranus, but also provides us with clues about its formation and evolution. The James Webb Space Telescope continues to exceed expectations and reveal more details about our universe every day. Its latest triumph is a series of images of Uranus taken very recently, which surpass even the impressive observations made in April 2020. In early 2023, the JWST provided us with unprecedented views of Uranus, allowing us to observe the atmospheric dynamics and ring system of the planet in a new light. However, the recent images go a step further. Not only are they sharp, but they reveal aspects of Uranus that were previously hidden or blurred, even in the April observations. Take the rings of Uranus as an example. The latest images show them more clearly, allowing us to observe finer structures within the rings and even detect faint dust bands that were previously invisible, such as the Zeta ring, the incredibly thin ring closest to the planet. The strength of the JWST lies not only in its punctual observations, but also in its ability to continuously track celestial objects. Continuous observations of Uranus have allowed us to observe changes in the planet's atmosphere, track the movement of its clouds, and observe the evolution of its storms over time. The changes in the polar regions are especially striking. The bright white layers and dark bands near the poles, whose origin is still unclear, have shown remarkable changes. This continuous observation provides very valuable data for understanding the seasonal changes and long-term weather patterns of Uranus. In the set of planets in our solar system, Uranus stands out for a peculiar characteristic, an extraordinary axial tilt, different from that of any other planet. Uranus rotates practically on its side, tilted at an angle of approximately 98 degrees. This unique orientation has long intrigued astronomers and has triggered a quest to understand its origin and consequences. To understand the significance of this inclination, we must travel back in time to the early days of our solar system. Probably, Uranus was formed with a much less pronounced inclination. The prevailing theory suggests that a catastrophic event, perhaps a collision with a planet-sized object, drastically changed its orientation. This colossal impact would have thrown Uranus to one side, changing the definition of its axis of rotation. Such a dramatic event in the planet's history likely not only changed its rotation, but also left an indelible mark on its entire system, including its satellites and rings. Today, this lateral rotation is a unique spectacle. Each pole of Uranus is alternately flooded with sunlight and plunged into darkness at intervals of 42 years. This extreme tilt gives rise to extreme seasons, different from those observed on other planets. The implications for planetary observation and research are enormous. The inclination of Uranus allows us to observe its rings and satellites from different perspectives, offering information about their composition and dynamics. For example, when the rings of Uranus are oriented towards Earth, they become almost invisible, revealing fainter dust bands and smaller satellites. Compare this to Earth, which is only tilted 23 degrees. 5 degrees, the extreme tilt of Uranus causes drastic changes in its weather patterns, making it a gold mine for scientists studying planetary climate. The inclination also affects the circulation of Uranus' atmosphere. Prolonged exposure to sunlight from the poles can lead to complex weather systems, as seen in recent images from a JWST. These systems are very different from those of other planets and constitute a unique laboratory for understanding atmospheric physics. Let us journey through a Uranian year. Each season on Uranus lasts about 21 terrestrial years, a consequence of its 84-year orbit around the Sun. This long duration means that each hemisphere experiences long periods of daylight, followed by equally long nights. As a result, the planet undergoes drastic changes in its appearance and climate, since a pole of Uranus enjoys uninterrupted sunlight during summer, while the opposite pole is submerged in a deep, dark winter. This marked contrast creates unique atmospheric conditions, causing complex meteorological patterns and climatic changes. The impact of these seasonal changes on the atmosphere of Uranus is profound. When the sun illuminates the surface of the planet, it heats the atmosphere, creating colossal storms and dynamic cloud systems. These atmospheric phenomena are not static, but evolve and change with the seasons, painting a changing portrait of the planet. Among the most striking characteristics are the bright peaks of the clouds that appear when the sun illuminates the atmosphere of the planet. These clouds, composed of frozen methane and other gases, reflect sunlight, creating a dazzling spectacle. On the contrary, dark spots of storms that look like giant hurricanes travel the surface of the planet. In addition, the planet's seasonal phenomena not only affect the planet itself, but also its moons. A recent study of Uranus's moons, or rather a particularly intriguing phenomenon, is the development of temporary atmospheres in these moons, a spectacle caused by the unique conditions of the Uranian system. The key to understanding these temporary atmospheres lies in the extreme inclination of the axis of Uranus and its effect on the orbits of the satellites. As these satellites orbit the planet, they experience drastic changes in solar exposure, alternating between long periods of intense sunlight and prolonged darkness. During the long summer, exposed to sunlight, the icy surfaces of these satellites undergo a process known as sublimation. The ice, composed mainly of water, methane, and carbon dioxide, is transformed directly from solid to gas, without passing through the liquid phase. This sublimation creates thin, temporary atmospheres, called exospheres, that envelop the satellites. These exospheres are more pronounced when the moons are warmer. Recent investigations by the James Webb Space Telescope show that this phenomenon is more dynamic and complex than previously thought. The exospheres are heterogeneous. They vary in composition and density depending on the moon's topography and the intensity of solar radiation. As the satellites enter their winter phase, the exospheres gradually dissipate. The gases recondense on the surface and return to an icy state. This cycle of creation and disappearance of the atmosphere is a unique characteristic of the satellites of Uranus, which opens a window to the interaction between solar radiation and surface ice. The rings of Uranus, often eclipsed by the majestic rings of Saturn, have their own history of intrigue and cosmic dynamism. A recent comparative study of the rings of Uranus, Saturn, and Jupiter sheds new light on these lesser-known, but no less fascinating, celestial characteristics. Unlike the wide and bright rings of Saturn, the rings of Uranus are narrow, faint, and less extensive, extending up to 4 planetary radii. This includes elusive rings like the Mu and the New rings. The study delves into the gravitational influence of Uranus's main satellites on these rings, a key factor in their formation and evolution. The significant influence of the 5 main satellites of Uranus, Miranda, Ariel, Yummel, Titania, and Oberon, plays a central role in the history of the rings. These satellites, much more massive than their smaller counterparts, dominate the gravitational dynamics within the Uranian system. Their positions and masses relative to Uranus provide a better understanding of the satellite's formation and the gravitational formation of the rings. The formation of Uranus's rings is attributed to a combination of processes that include collisions, the rupture of satellites, and the release of gas from the main satellites. These dynamic processes affect the material composition of the rings and are influenced by the constantly changing environment of the Uranian system. The stability of the rings is intrinsically linked to their dynamic interactions with Uranus's satellites. The study examines how accretion processes occur within the Roche limit and how the dynamics of the shepherd moons play a crucial role in maintaining the rings. In addition, The rings offer a unique opportunity to understand the internal structure of Uranus through seismological studies. The model's results show how these satellites shape the ring system, affecting its structure and stability over time. The model predicts a significant loss of material within the ring system, mainly due to the gravitational interaction with the satellites. The complex dance between the moons and the rings is a key aspect of the Uranian system. The dynamic exclusion zones created by the satellites and the influence of these zones on the distribution of the material of the rings are crucial to understanding the structure and evolution of the rings. The study also examines the role of interactions between satellites in the evolution of the system, especially the past resonances between satellites, such as Ariel and Umbella, and their impact on the orbits and geology of the satellites, especially Miranda. But the mysteries surrounding this planet do not end there. You have probably heard of the aurora borealis. Well, the latest discovery refers to the auroras of Uranus, which also has them. However, unlike those of Earth, these auroras occur in the infrared spectrum. Using the Keck telescope, astronomers observe an increase in the emissions of trihydrogen cations in the planet's atmosphere. This is a revolutionary discovery that sheds light on the magnetic field and the unique dynamics of Uranus's atmosphere. The magnetic field of Uranus, which deviates significantly from the axis of rotation of the planet, creates a unique coupling between the magnetosphere, the ionosphere, and the thermosphere. The detection of these infrared auroras is crucial because it opens a new window to these processes, so far unknown due to the lack of detections of this type on Uranus. The comparison of Uranus's polar auroras with those of Jupiter and Saturn reveals their different characteristics. Unlike Jupiter, where H3+ emissions have a short life that softens the variability of UV emission, Uranus's brightest infrared emissions do not necessarily coincide with the brightest ultraviolet emissions of the other planets. This unique aspect of the polar lights of Uranus provides valuable information for the study of exoplanets, especially for the worlds of warm ice giants. The study delves into the unusual hotspots observed on Uranus near the latitudes of the UV auroras. The analysis of these points in terms of temperature, column density, and total emission suggests that the increase is not caused by temperature, but by greater ionization, probably due to the activity of the polar auroras. The polar lights play an important role in warming the atmosphere, and on Uranus, the increase in H3+ emissions associated with these auroras indicates its participation in atmospheric processes. By studying these unique phenomena, we obtain a deeper understanding of similar processes in different planetary environments, which enriches our knowledge of how auroras shape planetary atmospheres, affecting not only thermal properties, but also the overall dynamics of the ionosphere and music, the magnetosphere. In the quest to unravel the mysteries of our solar system, the ice giants Uranus and Neptune are distant enigmas that merit more detailed exploration. Recent investigations, including a new analysis of Voyager images, have revealed that both planets actually have similar shades of blue-green color, radically changing our ingrained beliefs. Uranus and Neptune share many common characteristics. They are approximately the same size, the same mass, and are surrounded by deep atmospheres of comparable materials. However, for a long time, it was thought that their appearance was quite different. This error has now been corrected. Both planets are shown in their real colors, largely influenced by the methane layer of their atmospheres. The need for a dedicated mission to Uranus has never been greater. Such a mission would not only deepen our understanding of the planet itself, but also provide a comparative view of Neptune and other similar ice giants. Potential mission objectives range from studying the unique magnetic field and complex ring system to investigating the spherical dynamics of the atmosphere and internal structure. In a major achievement for planetary exploration, the Uranus Orbiter and Probe mission has been elevated to top priority for NASA's flagship mission within the 2023 to 2032 Planetary Science Survey. Future launch windows are available between 2030 and 2034. Key scientific objectives will include a detailed analysis of the unusual tilt of Uranus' axis and its effect on the planet's climate and weather patterns of the planet. The mission will also study the intriguing phenomenon of infrared auroras and their role in warming the atmosphere, providing a comparative study with other planets. The study of Uranus and Neptune will also provide valuable information on planetary evolution and dynamics, helping us understand why Uranus appears slightly whiter, perhaps due to its more stagnant atmosphere, which allows methane haze accumulation. This can tell us a lot about the atmospheric processes of ice giants. As we await a future mission to Uranus, we are on the threshold of discoveries that could redefine our understanding of the outer solar system. The exploration of this distant ice giant will not only unravel its mysteries, but also expand our knowledge of planetology, shedding light on the complex landscape of our cosmic home as a whole. The moon has always been a beacon of mystery and wonder, but beyond its radiant beauty and folklore, it hides secrets that have eluded us for centuries. Among these mysterious features is the lunar South Pole, a region shrouded in perpetual shadow and intense cold, untouched by any previous lunar mission. This is the story of India's Chandrayaan-3 on a journey to unknown territory. Launched on a journey of more than 238,000 miles, Chandrayaan-3 embarked on a mission not only of distance, but of discovery. Its goal was to unravel the mysteries of the moon's South Pole, a place where sunlight barely reaches, an area where the terrain is so treacherous that one must navigate an endless maze of craters and rocks. Here, in this alien landscape, Chandrayaan-3 was looking for answers to questions that have puzzled scientists for decades. What lies beneath the surface of this mysterious region? Do earthquake-like tremors shake this silent world? And the most exciting question is whether water, the elixir of life, exists here as ice. As Chandrayaan-3 ventured beyond Earth, it carried the aspirations of a nation and the curiosity of the world. Its main objective was clear, but difficult to achieve: a soft landing near the moon's South Pole, a feat that had never been achieved before. From the busy Mission Control Center of the Indian Space Research Organization, a team of dedicated scientists and engineers piloted this ambitious mission. Their expertise helped Chandra traverse the vacuum of space, overcoming the challenges of insertion into lunar orbit and descent. The South Pole of the Moon is a landscape unlike any other. Here, the terrain is a mosaic of craters and mountains, many shrouded in perpetual darkness. The challenge was not just to land, but to do so safely in an area where the terrain is unforgiving and most slopes are quite steep. When the Vikram lander separated from the orbiter, it began its descent. The lander, equipped with advanced sensors and engines, began its perilous journey to the moon's surface. Imagine a spacecraft autonomously navigating a maze of craters and rocks in search of terrain safe enough for landing. The lander's onboard systems worked tirelessly, analyzing every inch of the terrain that stretched out in this treacherous landscape. The lander also had to contend with extreme temperatures. The South Pole of the Moon is a place of extreme contrasts. The sun barely rises above the horizon, while the shadows hide frigid temperatures that can drop to minus 382 degrees Fahrenheit. As the lander made its final approach, the hearts in the Flight Control Center were pounding. Every second was decisive, every maneuver a test of human ingenuity and technological prowess. With a slight bump, Vikram landed, marking a historic moment not only for India, but for lunar exploration in general. In the silence of the moon's South Pole, Chandrayaan-3 began its mission of exploration and discovery. Thus, after the historic landing of Chandrayaan-3, a new chapter in lunar exploration began. The aim of the mission was to maximize the study of the moon's characteristics, especially its elusive exosphere and ionosphere, and to establish the range of temperature variations just beneath its surface. The lunar exosphere, the thin layer of gases surrounding the moon, holds the key to the satellite's past and present. Unlike Earth's robust atmosphere, it is so rarefied that it almost resembles a vacuum. Developed with the latest technology, The instruments of Chandra-3 are designed to measure the density and composition of this elusive layer. In addition to the exosphere, the mission delves into the lunar ionosphere. This layer, formed by the solar energy that ionizes the atoms of the exosphere, plays a crucial role in lunar communications and navigation. The measurements of Chandra-3 were designed to provide unprecedented information on the density and behavior of the ionosphere, which is important for future lunar missions and potential human habitats. Another intriguing aspect of the mission was the study of temperature variations just below the lunar surface using one of the 4 instruments of the landing module, the CHASTE, or Chandra Surface Thermophysical Experiment. The temperature probe, submerged in lunar regolith, had the critical mission of mapping the lunar soil's thermal profile. Chandrayaan-3's results revealed a strong contrast in surface temperatures during a lunar day. Temperatures rose drastically to 60 degrees Celsius. While at only 8 centimeters deep, they dropped significantly to minus 10 degrees Celsius, demonstrating that lunar soil is a potential thermal insulator. This discovery opened up new opportunities for future lunar habitats, as it suggests that the lunar regolith could serve as thermal insulation to protect astronauts from the harsh extreme temperatures and harmful radiation of the moon. These studies were more than simple scientific efforts. They were a step forward towards a future in which the moon could be a gateway to space exploration. The mission's findings on the exosphere, ionosphere, and lunar subsurface temperature laid the groundwork for understanding the moon's environment and its potential to harbor human life. In the vast lunar landscape, Chandrayaan-3 was ready to detect a phenomenon not observed in more than 50 years, a moonquake. The mission managed to shed light on one of the moon's most intriguing and least understood aspects. The Instrument for Lunar Seismicity, ILSA, a seismic instrument designed to detect the slightest tremors on the moon, achieved this. Chandrayaan-3 detected what appeared to be a moonquake. This is a significant discovery, as the last such observation was during the Apollo missions in the early 1970s. Moonquakes are fundamentally different from terrestrial earthquakes, since Earth's seismic activity is largely due to the movement of tectonic plates. The moon, lacking these plates, experiences earthquakes for various reasons. These tremors can last much longer than earthquakes, sometimes up to an hour, and their origin is a matter of scientific interest. The data from Chandrayaan-3 suggests several possible causes for these earthquakes. One theory is collision with meteorites, which could cause shock waves that penetrate the. Another is Earth's gravitational force, which causes tidal forces that load the lunar crust. Finally, extreme temperature fluctuations on the lunar surface can cause expansions and contractions that lead to earthquakes. These earthquakes are not just superficial phenomena, but are windows into the interior of the moon. By analyzing seismic waves, scientists can deduce the composition and structure of our satellite's interior, which resembles an ultrasound of the lunar interior. This information is of great importance for understanding the moon's formation and evolution. The detection of a moonquake by the Chandrayaan-3 spacecraft has not only provided a glimpse into the dynamic nature of our celestial neighbor, but has also opened up new perspectives on the geological processes that shape the moon to unravel the geological mysteries of the moon. Chandrayaan-3 carried out another exploration. Among the most intriguing findings is the discovery of sulfur, an element whose presence on the moon has been shrouded in mystery. The Laser-Induced Decomposition Spectroscope, or LIBS rover, a marvel of scientific instrumentation, vaporizes small samples of lunar soil using high-energy laser pulses. When the plasma emits light, the spectroscope analyzes its wavelength, thus revealing the presence of various elements, including sulfur. Sulfur on the moon is a significant finding. On Earth, sulfur is often associated with volcanic activity, raising questions about similar processes on the moon in the past. Its presence could provide information about the moon's volcanic history and the processes that shaped its surface. In addition to sulfur, another key objective of Chandrayaan-3 was the search for water ice, a search that has intrigued scientists for decades. Water ice on the moon is not only a scientific curiosity, but also a potential resource for future human missions, providing water for life support and fuel production. Despite high hopes, Chandrayaan-3, like its predecessors, found no direct evidence of water ice on the lunar surface. However, the lack of direct evidence is not a conclusion, but a clue leading to new hypotheses. One theory is that of the cold trap, according to which water vapor can migrate to permanently shadowed craters of the poles and freeze into ice. The detection of sulfur adds another layer to this theory, as sulfur can become trapped with water ice and released as a result of the decomposition of water molecules by high-energy solar radiation. The lack of direct evidence of water ice raises important questions. Is the ice located deeper below the surface, protected from detection by the insulating properties of the lunar soil, or is its prevalence more heterogeneous and difficult to detect than previously thought? During its exploration of the moon's south pole, the Chandrayaan-3 probe found something more than sulfur. The LIBS instrument of the rover performed the first in situ measurements of the elemental composition of the lunar surface in this region. In addition to sulfur, the instrument detected aluminum, calcium, iron, chromium, and titanium, each of which reflects part of the complex geological history of the lunar surface. Other measurements added new details to this discovery, further revealing the presence of manganese, silicon, and oxide. Each of these elements, with its own unique spectral signature, provided clues about the moon's formation and its evolutionary history. Studies on the presence of hydrogen, a key component in the search for water. The discovery of these elements and the mission's continued search for water ice underscore the dynamic and complex nature of lunar geology. Each discovery, each unanswered question, brings us closer to our nearest celestial neighbor and prepares us for the next steps in lunar exploration. The Chandrayaan-3 mission to the moon's south pole opened a new chapter in lunar exploration and also paved the way for the next ambitious leap. The LUPEX Lunar Polar Exploration Mission, by its English acronym. This joint venture between the Indian Space Research Organization and the Japan Aerospace Exploration Agency is scheduled to launch no earlier than 2026. LUPEX plans to send an unmanned lunar lander and rover to further explore the moon's south pole region. JAXA will likely provide the H-3 launch vehicle and rover, currently in development, and ISRO will provide the lander. This mission represents a significant step in international cooperation on lunar exploration. Are multifaceted. It will demonstrate new surface exploration technologies, fundamental for sustained lunar exploration in the polar regions. Precise landings will be achieved through the use of a feature matching algorithm and navigation equipment derived from the JAXA Smart Lander to investigate the lunar mission. The LUPEX rover will carry several instruments from JAXA and ISRO, including a drill capable of collecting samples at a depth of 5 feet, 15 meters. 5M. The search for and analysis of water are key objectives of the mission. The possible discovery of water ice could be a turning point for future lunar missions. Parallel to LUPEX, the RO Chandrayaan-4 mission is in the planning phase, designed to bring samples from the moon, with launch scheduled for 2028. Chandrayaan-4 will consist of 4 modules: a transition module, descent module, ascent module, and a reentry module. The ambitious goal of the planned mission is to bring back soil samples from the moon, which will provide invaluable information about the lunar environment. The mission will involve complex maneuvers, such as sample collection, docking in lunar orbit, and returning the samples to Earth. The innovative discoveries of Chandrayaan-3, from the detection of sulfur and other elements to the study of lunar earthquakes, have revealed new layers of the moon's mysterious nature. These results provide crucial information about the moon's geology, its internal structure, and the potential for future lunar habitats. Looking ahead, the future of lunar exploration looks promising. Missions like LUPEX and Chandrayaan, which build on the legacy of previous ones, will continue to explore the moon's mysteries. India's role in these efforts is not only that of a participant, but also as a pioneer. Events like these inspire us to look beyond to the infinite mysteries of the cosmos. Is the fabric of our universe woven with the threads of time travel, or is it a tapestry of unattainable dreams? Our documentary series embarks on a quest through the halls of science and imagination, exploring the limits of our understanding about the cosmos and our place in it. Can we bend time to our will, traversing the past and future as easily as we travel from one destination to another? We explore the tempting concept of time travel, delving into the realms of physics and fantasy to discover whether our universe harbors the potential for such extraordinary journeys. What barriers stand between us and the realization of a warp drive, a technology that could break the cosmic speed limits set by Einstein's theory of relativity? Theory of relativity. We investigate the scientific obstacles and advances that suggest the possibility of traveling faster than light, wondering what prevents us from building a warp drive in the cosmic ballet, where stars are born and black holes devour. The concept of white holes presents an intriguing counterpoint, a tantalizing possibility that challenges our understanding of astrophysical phenomena. Could these theoretical inverse black holes that expel matter and light into the universe actually exist? And what would their discovery mean for our understanding of cosmic evolution? Finally, we focus on a revolutionary discovery, a new law of nature that bridges physics and biology, offering a framework for predicting the course of evolution itself. How does this new law of nature redefine our understanding of life's complexity and its interaction with the physical universe? Join us as we explore these profound questions in search of answers at the intersection of known science and speculative theory. This series is an invitation to travel beyond the horizon of our current knowledge, to reflect on the mysteries that lie at the heart of existence. Welcome to a documentary experience where the impossible becomes a gateway to new realms of knowledge. Music. Music. Imagine a canvas of moments woven with threads of time and matter, extending infinitely in all directions and capturing every choice, event, and heartbeat. What if you could navigate this intricate fabric? What if you could go back in time, look to the future, or even change history's course? Time governs our lives, but it remains one of the most mysterious phenomena in the universe. We measure it, we chase it, but can we control it? The concept of time travel has intrigued humanity for generations, inspiring countless works of fiction and sparking rigorous debate. But what does science say? Can time travel ever move from the pages of science fiction to the annals of scientific fact? Einstein's theory of relativity opened the door to this possibility by suggesting that time is not a constant, but a variable that can be manipulated. Furthermore, there are black holes, cosmic phenomena so powerful that they could distort not only light, but also time itself. Did you know that astronauts aboard the International Space Station age more slowly than humans on Earth, even if only by a fraction of a second? This is not science fiction. It is a proven consequence of traveling at high speeds. So let's travel through the corridors of time and explore the scientific paradoxes and unlimited possibilities that one day could make time travel a reality. Welcome to a journey through time. Long before the advent of science as we know it, humanity was fascinated by the skies and passage of time. Ancient civilizations paid attention to the stars, the sun, and the moon, creating elaborate calendars and methods for measuring time. Transported to the modern era, this fascination finds a new canvas in film and literature. The concept of time travel has been a recurring theme, offering both escapism and a platform for intellectual curiosity. In 1895, H.G. Wells wrote the novel The Time Machine, which, by the way, not only popularized the term time machine, but also introduced the idea that one could navigate through time as through the dimensions of space. Then came Back to the Future, a pop culture phenomenon that took the concept of time travel and made it accessible to a new generation. Who could forget the DeLorean, the flux capacitor, the magnetic condenser, and the charming eccentricity of Doc Brown? Is charming eccentricity? But it's not just a Western phenomenon. The charm of time travel knows no cultural or linguistic boundaries, from Steins Gate in Japan to the profession of Ivan Vasilovich Chong in the Soviet Union. The theme of time travel resonates worldwide. So, what is it that attracts storytellers to this concept? The charm of rewriting history, the emotion of the unknown, or perhaps the philosophical questions that these journeys raise. It is a desire fueled by a mixture of nostalgia and expectation, a longing to relive fond memories or take a leap toward the promises of tomorrow. And now that we find ourselves on the cusp of scientific discoveries that could turn dreams into reality, the question becomes more important than ever. Could we, should we, and what would happen if we traveled through time? The blackboard is the canvas on which the abstract becomes possible. Here, equations like E=mc² are not just symbols, keys to understanding the universe, but could they unlock the secrets of time travel? From the big screen to living room televisions, time travel has been represented in countless ways. But let's set fiction aside and delve into the science that could make time travel more than just a plot device. Let's meet space-time, the four-dimensional fabric of our universe according to Einstein's theory of relativity. Einstein's theory of relativity. This fabric can be bent and deformed by mass and energy, but can it be torn or twisted to create a path through time? Time dilation, a consequence of Einstein's theory, suggests that time can flow at different rates depending on the speed of movement or the gravitational field. For example, astronauts on the International Space Station age slightly more slowly than people on Earth. Experiments with particles, accelerators, and atomic clocks have provided empirical evidence of time dilation. Particles traveling at speeds close to the speed of light have been observed to decay more slowly than their stationary counterparts. In addition, there are wormholes, hypothetical tunnels in space-time that, in theory, could shorten space and time. Although this is speculative, mathematics suggests they are possible. Leading physicists and cosmologists have expressed their opinions on the matter, offering theories ranging from the plausible to the utterly bizarre. Some even suggest that quantum mechanics, the science of the very small, could play a role in making time travel possible, and let's not forget black holes, the mysterious titans of space. Their enormous gravity is so strong that it distorts not only space, but also time itself. Could these cosmic phenomena be a gateway to other times? The scientific community is far from reaching a consensus. Time travel raises questions that challenge the very foundations of physics, from the nature of reality to the concept of causality. They say that time always moves forward and never backward. But what if we could take a leap forward, skipping decades, years, or even centuries? The idea might not be as far-fetched as it seems. When it comes to slowing down time, speed becomes the key parameter. According to Einstein's theory of relativity, the faster you move in space, the slower you move in time. So, could extreme speed be our ticket to the future? Believe it or not, time travel to the future has already occurred, albeit on a minuscule scale. Astronauts aboard the International Space Station experience time dilation and age slightly more slowly than their counterparts on Earth. Let's now focus on the twin paradox, the famous thought experiment that takes time dilation to another level. Let's imagine two twins separated at birth. One travels through space at a speed close to the speed of light, while the other remains on Earth. Upon reuniting, the space twin will appear younger. Reaching speeds close to the speed of light would greatly enhance this effect, but such speeds are currently beyond the reach of our technology, not to mention that the energy requirements would be astronomical. Scientists and engineers are tackling these problems by investigating propulsion technologies that could one day make it possible to travel at speeds near the speed of light. But even then, could the human body withstand such a journey? Let's imagine a future in which time dilation capsules are as common as airplanes, allowing people to jump into the future to glimpse advanced civilizations or even avoid catastrophes. Will knowledge of the future be a gift or a curse? And what will it mean for the concept of freedom? Music from science fiction to scientific articles, wormholes have captured our collective imagination. These hypothetical tunnels in the fabric of space-time could be the cause of the spatial shortcuts with which. But what are wormholes, and could they be the key to time travel? Let's imagine that we fold a piece of paper so that 2 points touch, and then prick it with a pencil in space-time. The wormhole would be that pencil, creating a direct path between two distant points. This concept gained popularity in the scientific community thanks, in part, to Carl Sagan, who, while writing his novel Contact, consulted physicist Kip Thorne to explore the scientific possibility of using a wormhole to travel between stars. Today, physicists are delving deeper into the mathematics of wormholes. While the general theory of relativity allows their existence, the equations also assume they collapse too quickly for anything to pass through. In theory, by introducing some exotic matter, for example, one could counteract the gravitational forces that cause a wormhole's collapse, keeping it open long enough for something or someone to pass through. The representation of wormholes in popular media often overlooks these complexities. They are usually represented as stable luminous vortices, but the reality, if they exist, may be much more volatile and unpredictable. Despite the lack of empirical data, the study of wormholes is a dynamic area of research. Scientists use computer models and indirect observations to understand their properties and potential uses. Imagine the possibilities of wormholes. They could be used to travel in time, with one end anchored in the present and the other in the future or the past. The implications for research and even for preventing global catastrophes are astonishing. Wormholes open the door to questions not only about where we could go, but also when. As we approach the possible discovery of these cosmic shortcuts, we must ask ourselves if we are prepared for the responsibility that comes with such power in the world of the very small, where particles are also waves and reality itself seems diffuse. In the quantum world, this region of uncertainty could contain the keys to unlocking time travel. Quantum mechanics challenges our everyday understanding of the world. Let's take the double-slit experiment, in which particles behave both as particles and as waves. Waves. This duality suggests that, at the quantum level, the structure of reality is much more malleable than we thought. Great minds like Richard Feynman and Niels Bohr have delved into the mysterious world of quantum mechanics, a theory that has been incredibly successful in explaining the behavior of matter and energy at extremely small scales. Some physicists suggest that quantum mechanics could offer a basis for time travel. The quantum tunneling effect, for example, allows particles to pass through barriers as if ghosts pass through walls. In the example of the tube, with two slits, can a similar principle allow time tunneling? Quantum computing is a new field that uses the principles of quantum mechanics to perform calculations at speeds unimaginable for classical computers. Some speculate that quantum algorithms could solve equations related to time travel that are currently too complex for current computers. The concept of quantum entanglement adds interest. Imagine two particles joined in a certain way. Once entangled, these particles become interconnected, forming a single quantum system. The truly amazing aspect of entanglement is that the state of one particle instantaneously affects its entangled partner, regardless of the distance that separates them, whether on the other side of the room or even on the other side of the galaxy. Change the spin of one, and the other changes instantaneously. Albert Einstein famously called it spooky action at a distance. At first, he liked this idea because it seemed to violate the speed of light limit established by his theory of relativity. However, since then, numerous experiments have confirmed that entanglement is a real and fundamental aspect of quantum mechanics. Could an effect at a distance like this make a difference in instantaneous time travel? Although the intersection between quantum mechanics and time travel remains a matter of speculation, it is a hot topic in scientific research. Researchers are studying everything from quantum loops in time to the role of quantum gravity in the early universe. Let's imagine a future in which the principles of quantum superposition could explain multiple timelines or realities. What if we could exist in a superposition of the past and the present? Could quantum mechanics be the final piece of the puzzle in our quest to conquer time? Let's move on from the world of the microscopic scale to a grandly large one. Black holes, mysterious titans of space whose gravity is so strong that not even light can escape them. But could these celestial phenomena hold the secret to time travel? Enter the concept of closed-time curves. A closed-time curve, or CTC, is a path in spacetime that repeats itself. In theory, an object, or even a person traveling along a CTC, could end up at an earlier point in time. The idea was first proposed by physicist Kurt Gödel in 1949. Gödel's solution to the Einstein field equation suggested that rotating universes could contain looped paths in time. However, these solutions required certain conditions, such as a universe full of rotating matter. Although the Gödel model is considered physically implausible in most cases, it has opened the door for other scientists to explore the concept. The main challenge is to find a scenario in which CTCs can exist without violating the laws of physics. One such scenario involves rotating black holes, known as Kerr black holes. The enormous gravitational and rotational forces can, in theory, twist spacetime into loops, creating CTCs, but there is a drawback. Most models predict that the center of a rotating black hole, known as a singularity, will be ring-shaped instead of point-shaped. This ring feature could potentially serve as a gateway to the CTC, but the powerful gravitational forces could also create a barrier known as the Cauchy horizon, beyond which the laws of physics are violated. The study of CTCs and black holes is fraught with paradoxes and uncertainties. For example, if the CTCs exist, they can give rise to paradoxes in which cause and effect are reversed. This has led some physicists to propose the chronology defense hypothesis, which suggests that the laws of physics prevent such paradoxes. Imagine the possibilities and dangers of approaching a spinning black hole. Could we safely navigate such a treacherous region of space-time? And if we could, what might we find on the other side? Another universe or another time? In addition to black holes and Tim-like curves, there is another cosmic mystery that could open a path through time: cosmic strings. These hypothetical one-dimensional cracks in the universe could be remnants of the Big Bang. Cosmic strings are believed to have formed in the early moments of the universe, as it cooled after the hot, dense state of the Big Bang. These strings would have been thinner than an atom, but incredibly dense with tremendous gravitational force. Although still theoretical, cosmic strings offer intriguing possibilities in time travel. Physicists J. Richard Gott and William Hiskok have significantly contributed to our understanding of these objects. Gott suggested that a cosmic string traveling at the speed of light could, in theory, distort spacetime enough to create a loop that would allow travel to the past or the future. However, the existence of cosmic strings remains debated. Their detection would require astronomical observations on scales exceeding our current capabilities. Furthermore, if they existed, harnessing their power for time travel would be quite a challenge. Let's return now to quantum entanglement. We have already explored how entangled particles are connected in ways that transcend ordinary spatial distances. Can they be united across time? Some theories suggest that entangled particles can be used to transmit information not only in space but in time. Let us imagine a future in which quantum entanglement is used to create a kind of quantum internet that allows instantaneous communication between eras. The intersection of cosmic strings and quantum entanglement is a frontier of theoretical physics, full of unanswered questions and untapped potential. Researchers explore how both phenomena could connect and what this means for our understanding of time travel. Imagine a scenario where cosmic strings are manipulated at the quantum level through entanglement. This would represent a fusion of the very large and small, a meeting point between cosmic and quantum scales that could revolutionize our concept of time travel. As we delve into the realm of time travel, we face many paradoxes and enigmas. These are not just intellectual exercises, but fundamental questions that may make time travel possible or impossible. First, there is the grandfather paradox. Imagine you go back in time and do not allow your grandparents to meet. If they never meet, one of your parents will never be born, and therefore, neither will you. But if you were never born, how could you have traveled in time? The grandfather paradox raises questions about causality and the very nature of time. Some theorists suggest that these paradoxes can be resolved by the existence of parallel universes where each solution generates a new timeline. Another confusing paradox is the so-called bootstrap paradox, which gets its name from the popular expression, pulling oneself up by one's bootstraps. Imagine going back in time to give Shakespeare a copy of your works, which he then claims as his own. In that case, where did those works originally come from? The bootstrap paradox creates a closed loop of cause and effect with no clear origin. It challenges our linear understanding of time, suggesting cause and effect may not be as simple as we thought. Think of another paradox, the predestination paradox, which occurs when a time traveler's actions in the past lead to the very event he was trying to avoid. This raises questions about free will and determinism, and whether we can truly change the course of history. The study of time travel paradoxes is not just a game for philosophers. It is an area of serious research in physics and metaphysics. Resolving these paradoxes could shed light on the possibilities of time travel. As we stand on the threshold of scientific discovery, the future of time travel remains a mystery shrouded in paradoxes, theories, and cosmic phenomena. What was once the realm of science fiction is gradually approaching real science, from cosmic strings to quantum entanglement, from rotating black holes to Tim-like curves. We explore the theories and possibilities that one day could make time travel reality. A reality. Current research is paving the way for new experiments, new technologies, and perhaps even a new understanding of the structure of reality. But as we teeter on the edge of cosmic horizons, one question becomes more important than all others. Are we prepared for what we might find? Time waits for no one, but what if we could wait on time? For years, it has been a concept defying the laws of physics as we know them, a dream that has given rise to countless stories and science fiction fantasies. This mystery is the search for a warp drive, a technology that could allow us to travel vast distances in space faster than light. Imagine a journey where the limitations of time and space yield to the power of human ingenuity, where the farthest corners of the universe become accessible. This is not just science fiction, but a puzzle that scientists have been trying to solve for decades. Since the physicist Miguel Alcubierre proposed a theoretical model in 1994, the Alcubierre model, a bold combination of imagination and Einstein's theories, offers a way to curve the fabric of space-time. But what is behind this bold idea? Is it just a fantasy, or could it be the key to unlocking interstellar travel? Today we explore the tangled web of problems and advances surrounding the warp drive, from the mysterious nature of negative energy to the horizon problem. So let's dive into one of the most intriguing scientific quests of our time, the quest for the warp drive. Science or fiction in the heart of Mexico City, amid the hustle of urban life, a young mind was fascinated by the mysteries of the cosmos. We're talking about Miguel Alcubierre, born in 1964, a physicist whose name has become synonymous with one of the most innovative ideas in theoretical physics. His journey began in Mexico and took him to the prestige we are talking about. Miguel Alcubierre, born in 1964, a physicist whose name has become synonymous with one of the most innovative ideas in theoretical physics. His journey began in Mexico and took him to the prestigious University of Wales, where he delved deeply into the fields of general relativity and cosmology. In 1994, while working at the Max Planck Institute for Gravitational Physics in Germany, Alcubierre made a revolutionary discovery in the perception of the world that challenged our understanding of space travel. Inspired by the iconic science fiction series Star Trek, he posed a bold question. Could the laws of physics allow for a real warp drive? Let's analyze the Alcubierre engine. Let's imagine a spacecraft that does not move through space in the usual sense, but is within a space-time bubble. This bubble, or warp bubble, is the key to the Alcubierre concept. According to Einstein's general theory of relativity, massive objects distort the fabric of space-time. Alcubierre hypothesized that if we could manipulate space-time in a controlled way, we could create a warp bubble. The space in front of the bubble is compressed, pushing it forward, while behind it the space expands, pushing it from behind. Inside this bubble, the spacecraft remains stationary, but the bubble moves, allowing the ship to travel faster than light without violating physics. This idea does not involve moving the spacecraft at high speed, but moving the space around it. It's like putting a surfboard, a spacecraft, on a wave, the warp bubble, and letting the ocean's space-time carry it. However, the Alcubierre model is not simply a manipulation of space, but requires exotic matter with negative energy density to stabilize it. This exotic matter is one of the many theoretical obstacles that scientists face when trying to turn the Alcubierre thruster from theory into reality. As we delve into the practical aspects of the Alcubierre thruster, we face enormous challenges that stand between theory and reality. The first of these is the scale of energy and mass requirements. It was originally thought that creating a warp bubble would require an amount of energy equivalent to the mass of the observable universe, an unimaginably enormous amount far beyond our current technological capabilities. However, the field of theoretical physics is constantly evolving. A notable achievement was when physicist Chris van den Broek proposed modifications to the shape of the warp bubble. These adjustments drastically reduced the energy requirements to approximately the mass of 3 suns, a colossal amount, but a significant step from the original estimates. The second major obstacle is the need for exotic matter and negative energy in the Alcubierre model. This exotic matter is crucial to stabilize the warp bubble and make it work as intended. Negative energy is a peculiar and controversial concept. It is a concept in physics that can distort the very structure of space-time. It is not simply the absence of energy, but a real physical quantity with negative characteristics. In the context of the Alcubierre engine, negative energy counteracts the effects of normal, positive energy, creating conditions necessary for the existence and stability of the warp bubble. Negative energy in the context of the Alcubierre engine is, without a doubt, a complex concept and somewhat difficult to understand in physics, and it is important to distinguish it from more familiar concepts such as gravitational potential energy in classical physics. The concept of negative energy often refers to gravitational potential energy. For example, the gravitational potential energy of an object in a gravitational field, such as a planet, is considered negative energy because work is needed to move the object from the source of gravity to a point where this energy would be zero, for example, to infinity. This form of negative energy is the cornerstone of our understanding of gravitational interactions in the universe. However, that necessary for anti-gravity propulsion is different. In this context, negative energy refers to a hypothetical form of energy whose density is less than zero. It is not just an accounting tool or a wave that describes the potential energy in a gravitational field, but rather a real physical substance or field with exotic properties, such as repulsive gravitational effects. This type of negative energy is not something we observe or understand well in the context of known physics. However, the existence of negative energy and, by extension, exotic matter remains a topic of intense debate and speculation in physics, although phenomena, such as the Casimir effect, suggest the possibility of the existence of negative energy under certain conditions. Harnessing it on the scale needed for the warp drive is a challenge. These challenges, the enormous energy requirements and the need for exotic matter, highlight the monumental task of transforming the warp drive from a theoretical model to a practical reality. They not only represent technological obstacles, but also fundamental questions about the nature of the universe and our ability to manipulate its basic forces. As we move towards the world of warp drive technology, we face another obstacle known as the horizon problem. This problem lies at the heart of the warp engine's design and poses serious issues for its practical use in astrophysics. The horizon is often defined as the boundary beyond which events cannot affect an outside observer. The most famous example is a black hole's event horizon, the point of no return. Beyond this horizon, the gravitational pull is so strong that nothing, not even light, can escape it. Similarly, for the warp engine, The horizon is the edge of a warp bubble. Inside this bubble, the spacecraft is isolated from the rest of the universe, just as the interior of a black hole is isolated by its event horizon from the outside world. The horizon problem stems from the unique structure of the warp bubble itself. In the Al-Kabri model, the spacecraft is in a region of the space-time plane surrounded by a warp bubble that compresses space in the front and expands it in the rear. This manipulation of space-time allows traveling at speeds greater than that of light, but with a critical limitation. It isolates the spacecraft from the rest of the universe. Imagine being located inside this warp bubble. The same mechanism that allows you to travel great distances in space also prevents you from controlling the ship and interacting with the outside world. Communication signals, navigation commands, and even visual observations are blocked by the bubble's limit. The passengers and crew will be unable to steer the ship, correct its course, or halt the trip once begun. The implications of the horizon problem are profound. It implies that a spacecraft, if powered by warp, would travel on a one-way, uncontrolled trip. This raises practical questions about the use of such technology for exploration or travel. How do we get to specific destinations? How do we avoid collisions with objects or adjust our path to handle unforeseen circumstances? In addition, this problem implies the need for a pre-established infrastructure similar to an interstellar highway, with mechanisms to control the warp bubble from outside. This requirement adds another layer of complexity to the already difficult task of making warp propulsion technology a reality. While the horizon problem represents a major engineering challenge, it is important to recognize that it does not invalidate the fundamental scientific validity of the concept. In theory, the principles underlying warp propulsion remain plausible within the framework of invalidates the fundamental scientific validity of the concept. In theory, the principles underlying the warp engine remain the same and plausible within the framework of the general theory of relativity. As we delve into the warp engine's complexities, we encounter another major issue, the radiation problem. This problem is twofold, as it involves both the accumulation of radiation at the front of the warp bubble and the potential effects of Hawking radiation within the bubble itself. First, let us consider the radiation that accumulates at the front of the warp bubble. As the bubble moves through space at a speed greater than that of light, it inevitably encounters interstellar particles in cosmic radiation. These particles in radiation, unable to pass through the warp bubble, accumulate near its leading edge. Such accumulation poses a significant risk when the warp bubble slows down or stops, as the accumulated radiation and particles are released in a burst of energy. The intensity of this release could be catastrophic, endangering not only the spacecraft and its passengers, but also potentially damaging any nearby objects of the destination moving within the warp bubble. We now encounter the second aspect of the radiation problem, Hawking radiation. This theoretical radiation, predicted by Stephen Hawking, arises from the effects of quantum mechanics near the edges of black holes. In the context of the Ailery drive, the intense deformation of space-time around the edge of the bubble could create conditions similar to those of the event horizon of a black hole, potentially generating Hawking radiation. This radiation could harm passengers inside the bubble, exposing them to high levels of energy and particles. The implications of these radiation problems are significant. Not only do they pose serious safety challenges, but they also raise questions about the feasibility of long-duration travel using the Alcubierre engine. Ensuring the safety of passengers and the integrity of the spacecraft against these radiation hazards is a critical area that requires further research and innovative solutions. It is a challenge that demands ingenuity and a deeper grasp of the interplay between quantum mechanics, relativity, and the harsh reality of space travel. When we turn our gaze to the current state of research in warp propulsion, we find ourselves in the midst of scientific inquiry. In recent years, numerous articles and theoretical papers have appeared, opening new paths in this field. A notable advance is the work of physicists who have revised the Alcubierre engine's energy requirements based on previous advances that significantly reduce the estimated energy. Recent articles have proposed several methods to optimize the warp bubble's geometry further. These improvements aim to make the energy requirements even more feasible, approaching the realm of possibility. Researchers such as Harold White, who played a key role in experimental work at NASA's Eagle Works laboratories on the feasibility of warp bubbles and space-time manipulation, have made significant contributions to this field. Another area of active research is the exploration of alternative theories that could circumvent some of the limitations of the Al-Kabir thruster. For example, some physicists are exploring the possibility of using solons, solitary waves that retain their shape as they travel at a constant speed, as a basis for creating stable warp bubbles without the need for negative energy. There's also growing interest in the role of quantum mechanics in the physics of the warp engine. Researchers are delving into the quantum aspects of space-time and how they might affect the warp engine's mechanics. This includes studying the effects of quantum entanglement and the potential use of quantum fields to stabilize the warp bubble. Recent theoretical advances also include the study of the effects of warp engine technology on causality and the structure of space-time. These studies are fundamental to addressing potential paradoxes and time travel scenarios, ensuring that the concept remains based on the laws of physics as we know them. Little by little, the dream of warp propulsion technology is getting closer and closer from the pages of science fiction to the realm of scientific possibilities, driven by the tireless efforts of researchers around the world. As we reflect on the future of warp propulsion technology, we stand at a crossroads of assumptions and possibilities. The realization of the warp propulsion, a concept that before was limited to the scope of science fiction, depends on several advances and key discoveries. In the first place, it is necessary to address the theoretical problems associated with the warp propulsion technology. This includes finding viable solutions to the enormous energy requirements, the creation and stabilization of warp bubbles, and the safe management of radiation risks. Advances in areas like quantum mechanics, exotic matter, and energy manipulation are fundamental to converting these theoretical possibilities into practical reality. Beyond the scientific and technical obstacles, the arrival of warp propulsion technology brings with it many ethical and practical considerations. The capacity to travel great distances in space at unprecedented speeds would revolutionize space exploration and open new horizons for humanity. However, great power carries great responsibility. The ethical implications of this technology must be carefully considered. This includes the potential impact on space ecosystems, the responsibility to explore and possibly interact with extraterrestrial life, and equitable access to this technology among nations. In practice, warp propulsion technology could lead to new methods of resource utilization, new ways to carry out scientific research, and even the possibility of interstellar colonization. This would fundamentally change our relationship with space, from exploration to habitability and utilization. For now, we look forward to a future in which the stars are not only points of light, but destinations within our reach in the night sky. This future promises unexplored territories and unprecedented exploration, inviting us to continue our search for knowledge and discovery. Music. There's an interesting mystery in our world generated by Einstein's equations of general relativity. It is the theoretical analog of the black hole that many know. We call it a white hole. Let's imagine a region of space in which, unlike a black hole that consumes everything, nothing can enter. Instead, this cosmic anomaly defies our expectations by expelling matter and energy that shine intensely on the dark canvas of space. In a universe governed by the concept of an arrow of time, where events flow from the past to the future, a white hole is a tempting paradox. It is like watching a movie in reverse, where the rules of gravity and time seem rewritten. But are these celestial wonders only mathematical curiosities, or do they contain the key to understanding the deepest truths of our universe? Let's delve into the mysteries of white holes by exploring their theoretical foundations, their enigmatic characteristics, and their potential role in the universe's history. At the beginning of the 20th century, Albert Einstein revolutionized our understanding of the universe by creating the theory of general relativity. This revolutionary theory proposed a radical idea. Gravity is not a force that attracts objects, but a curvature of space-time caused by mass and energy. Let's imagine space-time as a fabric stretched like a trampoline. When an object with mass, like a star or planet, lands on this fabric, it causes a depression. This curvature directs the movement of other objects that move along curved trajectories in space-time. This is gravity as Einstein imagined it. Einstein's theory led to the discovery of black holes, regions of space with a gravitational force so strong that nothing, not even light, can escape from them. These cosmic giants are formed when massive stars collapse under their own gravity, distorting space-time to the extreme. We present Carl Schwarzschild, a brilliant physicist who, while fighting in the First World War, found a solution to Einstein's equations. The Schwarzschild solution described the space-time around a non-rotating spherical mass, such as a star. Schwarzschild's work laid the foundations for understanding black holes, but also hinted at something even more mysterious. If a black hole is a region from which nothing can escape, could its opposite exist, a region in which nothing can enter, only exit? This gave rise to the concept of a white hole. Just as a black hole is the end point of gravitational collapse, a white hole can be considered an inverse black hole, a cosmic source that expels matter and energy. However, unlike black holes, which have already been observed, white holes remain a theoretical concept, a tempting possibility in the vast cosmic mystery of astrophysics. The path from mathematical abstraction to physical reality is often long and difficult, and white holes are no exception. These theoretical entities arise from the complex equations of general relativity, the same mathematical structure that predicts the existence of black holes. The mathematics of white holes are solid, but it seems like a puzzle with missing pieces. We understand its theoretical basis, but the real challenge is relating these mathematical models to observable phenomena. Let's imagine a universe in which, instead of collapsing inward, a region of space-time does the opposite. It explosively expels matter and energy. This is the essence of a white hole, a mirror image of a black hole in which the flow of time and matter is reversed. But can these mathematical abstractions exist in our physical reality? The debate among scientists is continuous and multifaceted. Some theorists suggest that white holes may be remnants of the early universe, exotic structures interwoven into the fabric of space-time. Others suggest that they may represent the other end of a black hole, a cosmic exit door from which matter and energy reappear after being swallowed by the black hole. The novel idea of quantum gravity suggests that, as a black hole evaporates over eras and loses mass, it may reach a point where it can no longer sustain itself. At that moment, it can become a white hole and release the trapped content back into the universe. However, there are serious problems with the physical existence of white holes. The laws of thermodynamics, especially the concept of entropy, pose a serious obstacle. Entropy, a measure of disorder, tends to increase in the universe, while white holes, by nature, decrease entropy, contradicting this principle. Furthermore, the stability of white holes remains a controversial topic. Some theories suggest that, if they were formed, they would be extremely unstable and would probably collapse almost instantaneously into black holes in outer space. White holes represent one of the most paradoxical and enigmatic concepts. These mirror images of black holes have characteristics challenging our traditional understanding of physics. Let us understand in more detail the concept of a white hole in theoretical physics. At the center of a white hole is its event horizon, not of inescapable attraction as in black holes, but of impenetrability. This event horizon marks the point at which matter and energy are expelled, creating a spectacle of cosmic scale. Unlike black holes, which absorb everything, a white hole is a source of expulsion, the cosmic source from which matter and energy arise. One of the most intriguing aspects of white holes is the concept of time reversal. Time usually flows in one direction, from the past to the future. However, white holes seem to reverse this flow. It is like watching a science fiction movie played in reverse, where the usual rules of time and space are inverted. As we delve into the nature of white holes, we face a realm of paradoxes and problems. One of the most important problems is its connection with the entropy mentioned above. According to the second principle of thermodynamics, entropy, or the measure of disorder, must always increase within a closed system. However, white holes seem to ignore this law, decreasing entropy and expelling matter in an ordered state. This apparent violation of the laws of thermodynamics presents a serious problem to our understanding of physical processes in the universe. How can an object like a white hole exist if it contradicts such a fundamental principle? Another paradox lies in the concept of the arrow of time, according to which the universe advances inexorably forward. White holes suggest a scenario in which time can flow backwards, at least from a certain perspective. This concept breaks not only our understanding of time, but also the very nature of causality. Let's summarize the characteristics of white holes: their event horizons, the expulsion of matter, and the concept of time reversal present a fascinating but paradoxical panorama for the theories that, although we seek to solve these problems, white holes remain in the realm of theoretical physics. As we delve into the mysteries of the cosmos, the concept of white holes invites us to rethink our understanding of the universe. These theoretical objects are not only surprising anomalies, but may have profound cosmological implications. Let us consider the Big Bang, the colossal explosion that marked the beginning of our universe. Some theorists suggest that this crucial moment in cosmic history was not just a random explosion, but that the event may have been a white hole of unimaginable magnitude, an eruption of matter and energy that gave rise to the cosmos. This vision offers a radically new interpretation of the origin of our universe, suggesting that white holes could play a role in cosmic genesis. Let us imagine a white hole not only as a theoretical construction, but as the very source of the creation of our universe. In this scenario, the Big Bang could be conceived as a white hole of immeasurable scale that expelled matter, energy, and space-time, which subsequently evolved into the stars, galaxies, and planets that we observe today. This vision offers a radical rethinking of the Big Bang. Instead of an indefinite singularity, we have a white hole, an entity defined by the laws of physics, or in a way that stretches our understanding to the limit. This white hole could have been the first spark that set the stage for subsequent cosmic evolution. If the Big Bang was really a white hole, profound questions arise about the nature of our universe. What was the origin of this white hole? Was it the result of a collapse of the universe from another dimension, or the result of processes that surpass our current scientific understanding? This concept also changes our perception of time and causality. If the Big Bang was a white hole, it suggests the existence of a universe with a more complex timeline in which the beginning and end of cosmic phenomena are intertwined in ways that we still do not yet understand. This idea of the Big Bang as a white hole combines organically with the Big Bounce theory, according to which the beginning of our universe could be the result of the collapse of a previous universe. This gives rise to the idea of cyclic universes, suggesting that each cosmic end can give rise to a new beginning similar to the explosive genesis of a white hole. The existence of white holes could also confirm the concept of parallel universes. If white holes can expel matter and energy, could they be a gateway to other universes? This possibility is related to the multiverse theory, which postulates the existence of multiple universes, possibly infinite, alongside our own. In parallel universes, there could be different versions of physics, alternative histories, and perhaps even variations of ourselves. Another intriguing connection relates to wormholes, hypothetical tunnels in space-time. Theoretical models suggest that wormholes could connect distant regions of space and perhaps even different universes. If white holes are connected to wormholes, they could serve as cosmic portals that open paths to remote corners of the universe or to other dimensions. Together, this connection raises tantalizing questions about the nature of space and time. Could white holes and wormholes allow travel through vast cosmic distances or even between universes? Looking towards the future of astrophysics, we see that, at this moment, there's a lot of scientific research that, in one way or another, affects the subject of white holes, but two research articles stand out from the rest, shedding light on the mysterious nature of these cosmic objects and offering new ideas and possibilities that could revolutionize our understanding of white holes. The first article takes us on a journey to the edge of black and white holes, exploring the close connections between them and refocusing attention on the physics that occurs near their horizons. The authors introduce the concept of horizon-penetrating coordinate systems, a revolutionary approach that allows us to distinguish between the horizons of black and white holes. These differ from standard curvature coordinates in a small region near the horizon to emphasize the distinction between black and white horizons, which depends on the physics near the horizon. The study suggests that black holes might not be the cosmic dead ends that we once thought, but rather could be in quantum superposition with white holes, creating a scenario in which observed phenomena could hint at the existence of these white theoretical counterparts. The article also delves into the role of quantum physics in these regions near the horizon, suggesting that quantum effects may dominate, which has important implications for our understanding of white holes. However, the authors emphasize a problem in observational astrophysics, in which there is substantial observational evidence of the existence of black holes, but relatively weak observational support for white holes. Moving on to the second article, entitled New Black to White Hole Solutions with Improved Geometry and Energy Conditions, we find that the attention here is focused on how to convert black holes into white holes. Guided by the principles of quantum gravity, this study presents models in which the effects of quantum gravity prevent the formation of singularities within black holes, providing a smooth transition to white holes. This resolves the age-old paradox of information loss by assuming that matter can pass through a black hole and appear in a white hole. The article also explores the geodesics within these models, confirming the completeness of the particle trajectories and the transition from the black hole region to the white hole region. This supports the idea of a continuous and unhindered flow of matter, changing our understanding of these cosmic phenomena. By integrating these theoretical developments with emerging technologies, we find ourselves on the threshold of a new era in astrophysics. The future of research on white holes promises to reveal new aspects of the universe, where the boundaries between quantum mechanics and general relativity blur. In summary, we can say that the future of research on white holes looks very promising. Who knows? Perhaps very soon we can discover indirect evidence of the existence of these intriguing objects. Our universe hides a mystery that has long captivated the human mind, a question that bridges the known and the unknown, the simple and the complex. Here, on Earth, life thrives in a continuous movement of order and chaos. Every form of life is evidence of a hidden order, a pattern woven into the very fabric of existence, from the smallest microorganisms to the largest mammals. But what if the complexity of life, the very essence of our existence, could be explained not only through the lens of biology, but through a mathematical framework? This is the territory of assembly theory, a revolutionary concept that transcends traditional science. It is a journey into a world where mathematics and biology converge to reveal the hidden architecture of life. Imagine a universe in which the most recondite secrets of life, from the simplest molecule to the most complex organism, are encoded in mathematical language and waiting to be deciphered, where the line between the living and the inert blurs, giving rise to new possibilities and knowledge. Let's explore how this revolutionary idea is changing our perception of life, evolution, and the cosmos itself. And perhaps we can even get closer to answering the fundamental question: what is the true nature of life in the universe? Since the dawn of civilization, mathematics has been the language of the universe, a tool to decipher the mysteries of nature. But how does this language of numbers and equations relate to understanding the very essence of life at its core? Assembly theory offers a simple but profound idea. The complexity of life can be measured and understood through a mathematical prism. Let's think of life as a puzzle in which each piece represents a molecular building block. Assembly theory seeks to show how these pieces come together step by step to form the complex structures that define living organisms. Each step in this assembly process represents a leap in complexity, from simple atoms to complex proteins. The theory introduces the concept of the assembly index, the cornerstone of this theory, which measures the number of steps needed to build a biological structure. It is a numerical value that captures the essence of complexity by quantifying the immeasurable. But how does the standard model of physics fit into this? The standard model of physics describes the fundamental particles and forces that govern our universe. It seems completely separate from the complexities of biology. However, assembly theory bridges both fields. In the field of assembly theory, the standard model lays the foundation for understanding forces and interactions. It is a bridge between the microscopic world of quarks and leptons and the macroscopic world of living beings. Another important element of the theory is the concept of studying dynamic systems, the phase space. This is a mathematical concept used to describe all possible states of a system in the context of assembly theory. The phase space allows us to trace the path of the assembly of life from a single point, representing the simplest form of life. The phase space expands, branching into almost infinite possibilities, and each path represents a different route that life can take in this unlimited mathematical landscape. The trajectories of evolution and its complexities unfold in this mathematical framework, which offers us a new perspective on the complexity of life. It is not only about the particles and forces described by the standard model, but about how these elements combine and interact over time to create the diverse pattern of life that we see around us. This is where the chaos of random molecular interactions gives way to the order of living structures. So let's ask ourselves this question: are the complexities of life simply a product of chance, or is there a deeper cause? Let's consider two very contrasting concepts: complexity and entropy. Entropy, a measure of disorder and randomness, seems to contradict the complexity we observe in life. How do these opposing forces coexist in the natural world? This is where assembly theory offers a revolutionary perspective. A central element of assembly theory is the assembly index, a revolutionary tool designed to measure the complexity of life. Think of it as a cosmic ruler that measures the steps needed to assemble a biological structure from its simplest components. Imagine a single molecule as the starting point on this scale. As you ascend the scale, each step represents a more complex assembly, from molecules to cells and beyond. The higher the index, the greater the complexity and the less likely the structure is to have arisen by chance. Now let's delve into the interaction between entropy and delve into the interaction between entropy and complexity. Entropy, a concept rooted in thermodynamics, suggests that systems tend to disorder. However, life defies this tendency, evolving from simple origins into a variety of complex, combined forms in the ordered structures that we see today. How does assembly theory resolve this contradiction? It suggests that life inherently is a process of overcoming entropy. Through the assembly index, we see that life's complexity isn't a challenge to entropy, but a journey through it. Let's consider the primitive Earth, a broth of simple molecules that, over millennia, driven by the laws of physics and chemistry, began to assemble primitive Earth, a primordial broth of simple molecules. Over millennia, driven by the laws of physics and chemistry, these molecules began to assemble into more common complex structures. Each step marked a victory over entropy, a step towards greater complexity in life. By rethinking evolution through assembly theory, we see it not as a mere biological process, but as a mathematical inevitability. The emergence and evolution of life became a story of increasing complexity, one written in the language of mathematics. Music. Let's move on now to a very trivial question, but one that is presented in a new light. Are we alone? The search for extraterrestrial life has captivated our imagination for centuries. Now, thanks to assembly theory, we have a new tool in this search. Assembly theory offers a unique approach to detecting life. It is not about scanning the sky for radio signals or analyzing light spectra for oxygen, but about understanding the complexity of molecules and structures that indicate life. Let's imagine we scan the atmosphere of a distant exoplanet or the surface of a moon in our solar system. Using assembly theory, we could analyze the molecular complexity of samples for patterns that indicate life's presence. The higher the assembly index, the more likely it is that these molecules are the result of life and not of random processes. Music, however, the path to the discovery of extraterrestrial life is full of challenges and limitations. One of the biggest obstacles is our understanding of life itself. Our definition of life is based on what we know of life on Earth. What if it doesn't meet our biochemical standards? Another problem is the immensity of space. The universe is vast, and our ability to explore it is limited by current technology. Even with the most sophisticated telescopes and probes, we can analyze only a small fraction of the cosmos. In addition, assembly theory, although powerful, is still in its infancy. It is a new approach, and its application to the search for extraterrestrial life is uncharted. There are doubts about its applicability and precision in different environments, especially those very different from terrestrial ones. Despite these problems, assembly theory's potential in the search for extraterrestrial life is enormous. It could redefine our understanding of life in the universe and open new doors in astrobiology. Thus, assembly theory offers a new way of seeing life, not only as a biological phenomenon, but as an emergent property of cosmic complexity. Let's imagine the early days of our planet, a world in motion, a melting pot for life's chemistry. Here in this chaotic environment, simple molecules began their journey of assembly, a process governed by the laws of physics and chemistry, but leading to something much deeper: life. According to assembly theory, life arises when these molecular structures reach a level of complexity that allows them to store and reproduce information. This is where chemical memory comes into play, a crucial step in life's evolution. Chemical memory is the ability of certain molecular structures to recover their structure. In other words, we can say that it is the blueprint of life in the world of assembly theory. This is where reproducibility becomes key. The ability to reproduce these patterns, to transmit them from generation to generation, is what drives the evolution of life, from the simplest RNA molecules and primordial soup to the great diversity of life we see today. Each step in this evolutionary journey has been a step forward in the assembly index. Each increase in complexity represents a triumph over the entropy that governs the universe. But the story of the origin and evolution of life is not only a story of increasing complexity, it is also a story of resilience and adaptability. Life has found a way to thrive in the most extreme environments, from the ocean's depths to the confines of space. In scientific discovery, each new theory is analyzed and debated. Assembly theory, a concept that promises to revolutionize our understanding of life and complexity, is now at a crossroads, questioned by critical voices such as Dr. Hector Zinel's. The criticism presented by Zinel raises fundamental questions about the future evolution of assembly theory. Encompassing an impressive 18,000 words, the article will require time and reflection, approximately between 1 and 2 hours of dedicated reading. This is not a superficial review of the subject, but a deep immersion into the heart of the scientific debate. For those interested, we leave a link in the description to both articles, the study and the counterarguments to it. Looking ahead, assembly theory's role in scientific research remains uncertain. Will it be able to adapt to and overcome these challenges, or will it remain a footnote in science history? Despite the disagreements, one thing is clear. The debates around the assembly theory have initiated a conversation about the nature of scientific discovery. These debates highlight the need for transparency, rigor, and humility when pursuing knowledge. In the end, the impact of assembly theory on future research may lie not in its specific claims, but in the lessons it teaches us about the scientific process. As we explore the mysteries of life in the universe, these theories will come and go, but the search for understanding and to unravel the mysteries of our existence will always remain the center of interest in scientific research.